imagine standing at the edge of an abyss, a place of such profound emptiness that it seems to contain nothing at all. No light, no sound, no matter, not even the familiar framework of space and time. This is the conceptual void from which our entire universe, in all its vastness and complexity, is thought to have been born. It is the ultimate mystery, the question that has haunted philosophers, poets, and scientists for millennia. Why is there something when there could have been nothing? As you gaze up at the star-dusted canvas of the night sky, you are not just looking at distant points of light, you are looking back in time, at the echoes of a cosmic story that began with a mystery so deep it challenges the very limits of human understanding. And yet, modern physics has begun to peel back the veil of this nothingness, and what it has found is not an empty, passive stage, but a vibrant, seething, and endlessly creative reality. The void is not a void. It is a quantum sea, a turbulent ocean of energy and potential, a place where the rules of our everyday classical world dissolve, and a stranger, more fundamental logic takes over. This is the realm of the quantum vacuum, a place where particles can be in many places at once, where they can be connected across vast, cosmic distances in an instant, and where the very act of observation seems to shape the nature of reality itself. This strange and beautiful vision of a potent, creative emptiness is not a new idea. It is a concept that has resonated through human history, an intuition that has found expression in some of our most ancient philosophical and spiritual traditions. The ancient Greeks spoke of chaos, the formless, primordial abyss that existed before the ordered cosmos. In the rich contemplative traditions of the East, we find even more striking parallels. The Hindu concept of shunyata, often translated as emptiness or voidness, is not a nihilistic concept of non-existence. It is the understanding that all phenomena are devoid of any fixed, independent self-nature, and that they arise from a common, underlying ground of being that is itself empty of any inherent characteristics, yet full of infinite potential. The Tao Te Ching, the foundational text of Taoism, begins with a meditation on the Wu, the unnameable formless void that is, paradoxically, the mother of the 10,000 things, the entirety of the manifest world. It is a remarkable convergence of thought that these ancient, intuitive cosmologies, born from deep introspection, seem to be pointing towards the same fundamental truth that modern physics is now uncovering through the rigorous language of mathematics and experimentation. Quantum mechanics, that strange and wonderful pillar of modern science, has given us a new language to describe this creative void. It tells us that even in a perfect vacuum, a space cooled to absolute zero and shielded from all external influence, there is an incessant, irreducible quantum jiggle. This is the world of quantum fluctuations, a place where pairs of virtual particles and their antimatter counterparts are constantly bubbling into existence, borrowing a tiny amount of energy from the vacuum for an immeasurably short time before annihilating each other and returning their borrowed energy to the void. This is not a theoretical fantasy. It is a direct consequence of one of the most fundamental principles of nature, Werner Heisenberg's uncertainty principle. Formulated in 1927, this principle states that there is an irreducible trade-off in our knowledge of certain pairs of properties of a quantum system. The more precisely you know a particle's position, the less precisely you can know its momentum. This fundamental uncertainty means that no region of space can ever be truly, definitively empty. The very act of measuring a region to confirm its emptiness would, by the uncertainty principle, inject energy into it. At the most fundamental level, there is no such thing as a truly empty or static space. Every point in the cosmos is permeated by a web of quantum fields, one for each type of fundamental particle. These fields are never completely at rest. They are always vibrating, always fluctuating, even in their lowest energy state. This irreducible minimum energy of the vacuum is known as zero-point energy. It is the baseline hum of the universe, the silent, ever-present music of the void. And this is not just a mathematical abstraction. The physical effects of these virtual particles and their zero-point energy can be measured. The Casimir effect, predicted by the Dutch physicist Hendrik Casimir in 1948 and later confirmed experimentally, shows that two uncharged parallel metal plates placed very close together in a vacuum will be pushed together by an invisible force. This force is not gravity, nor electromagnetism. It is the pressure of the quantum vacuum itself. The space between the plates can only accommodate virtual particles of certain wavelengths, while the space outside the plates can accommodate all wavelengths. This creates a pressure differential, a net force pushing the plates together. The void itself can exert a physical force. It is a stunning, tangible demonstration that what we call emptiness is, in fact, a dynamic, energetic, and powerful medium. The creative potential of this quantum vacuum is not limited to the fleeting dance of virtual particles. It may be the very source of our entire universe. The theory of cosmic inflation, one of the cornerstones of modern cosmology, proposes that in the first fraction of a second after the Big Bang, the universe underwent a period of hyper-accelerated, exponential expansion. The driving force behind this inflation is thought to have been the energy of a quantum field, known as the inflaton field, trapped in a high-energy, the false vacuum state. As this field relaxed to its true lower energy state, it released its stored energy, flooding the nascent universe with the matter and radiation we see today. In this picture, the universe is a kind of macroscopic quantum fluctuation, a bubble of reality that was inflated to cosmic proportions by the energy of the void. This idea leads to an even more mind-boggling possibility, the quantum foam. First envisioned by the physicist John Wheeler, this is the idea that at the smallest possible scales of distance, the so-called Planck length, an unimaginably small 10 to the power of minus 35 meters, the very fabric of space-time is not smooth and continuous, but a chaotic, turbulent foam of microscopic black holes and wormholes, constantly being created and annihilated by quantum fluctuations. At this fundamental level, our familiar notions of space and time break down. This is the realm of quantum gravity, the yet-to-be-discovered theory that will unify Einstein's general relativity with quantum mechanics. In this foamy quantum reality, a sufficiently large fluctuation could, in principle, give rise to a new, expanding universe. Our cosmos could be a single, fortunate bubble that emerged from this infinite, eternal sea of quantum potential. This is the scientific version of a universe from nothing, a concept explored by physicist Lawrence Krauss. The nothing in this context is not an absolute philosophical void, but the rich, dynamic, and endlessly creative quantum vacuum. This completely inverts our classical understanding of reality. We no longer see the void as a passive, empty stage upon which the cosmic drama unfolds. We see the void itself as the primary actor, the generative source, the mother of all that is. The emptiness between the stars is not an absence. It is the presence of an infinite potential, a potential that, some 13.8 billion years ago, blossomed into the vast, complex, and beautiful universe we call home. And so, as you lie in the quiet of the night, as your consciousness begins to drift into the silent, inner space of sleep, you are, in a sense, returning to this primordial state. You are entering your own personal quantum vacuum, a space of pure potential, a space where new thoughts, new dreams, and new realities can be born from the creative silence of your own being. In the early 1980s, the standard Big Bang model, while remarkably successful in describing the evolution of the universe from a hot, dense state, was facing a series of deep, conceptual puzzles. It was like having a perfectly working car, but with no idea how the engine was built or why it had started in the first place. Then, on a cold December night in 1979, a young American physicist named Alan Guth, poring over his equations, had what he later called spectacular realization. He had stumbled upon the cosmic ignition key. The theory he conceived that night, the theory of cosmic inflation, would not just solve the lingering puzzles of the Big Bang, it would fundamentally reshape our understanding of the first, infinitesimal moments of creation. And it would do so by unleashing the immense creative power of the quantum vacuum. The story that inflation tells is one of almost unimaginable drama. It proposes that in the very first flicker of time, between roughly 10 to the power of minus 36 and 10 to the power of minus 32 seconds after the Big Bang. The universe underwent a period of astonishing, hyper-accelerated, exponential expansion. It was a cosmic growth spurt of truly epic proportions. During this fleeting, almost timeless instant, the size of the universe increased by a factor of at least 10 to the power of 26, a number so large it is difficult to represent with analogies. It is like taking an object smaller than a single proton and stretching it to the size of a grapefruit in a time far shorter than it takes light to cross that same proton. This is not just an expansion in space. It is an expansion of space itself, a stretching of the very fabric of reality at a rate that completely dwarfs the speed of light. The engine that powered this explosive growth, according to inflationary theory, was the energy of a quantum field, dubbed the inflaton field, which was momentarily trapped in a high-energy, unstable state known as a false vacuum. Imagine a ball perched precariously in a small divot at the very peak of a vast, steep hill. It possesses a huge amount of potential energy, and it is in a state of metastable equilibrium. A tiny quantum jiggle is all it would take to send it cascading down the hill, releasing its stored potential energy as the kinetic energy of motion. The false vacuum of the early universe was like this ball at the top of the hill. It was a state of incredibly high and uniform energy density, and this energy had a peculiar and powerful property. It exerted a strong negative pressure, which, according to Einstein's theory of general relativity, creates a powerful gravitational repulsion. It was this anti-gravity of the false vacuum that drove the exponential, inflationary expansion. Eventually, this false vacuum state decayed, like the ball rolling down the hill, into the true, lower energy vacuum state of our current universe. This process, called reheating, was a cataclysmic event. The immense energy that had been stored in the inflaton field was released, flooding the now vast, empty universe with a hot, dense, and uniform soup of fundamental particles and radiation. This is the starting point of the standard, hot Big Bang model. Inflation, in this sense, is not an alternative to the Big Bang. It is a prequel, a brilliant and necessary prologue that sets the stage and explains the seemingly miraculous initial conditions from which the rest of cosmic history unfolded. The true elegance of inflationary theory lies not just in its dramatic narrative, but in its remarkable ability to solve the deep, conceptual puzzles that had plagued the standard Big Bang model. One of the most profound of these was the horizon problem. When we observe the cosmic microwave background CMB, the faint, relic radiation from the infant universe, we find that it has an almost perfectly uniform temperature in all directions, to an accuracy of about 1 part in 100,000. This is a profound mystery. In the standard Big Bang model without inflation, regions of the sky that are on opposite horizons today were never in causal contact with each other. They were too far apart for light, or any other signal, to have traveled between them in the time since the beginning of the universe. So, how could they have possibly reached the same temperature? It is as if you walked into a vast, cavernous room and found that the temperature at every single point was identical to within a tiny fraction of a degree, without any heating or cooling system to have ever been turned on. Inflation provides a beautifully simple solution. Before the period of exponential expansion, the region of space that would eventually become our entire observable universe was an incredibly tiny, subatomic patch. It was so small that it was in perfect causal contact with itself. There was plenty of time for all parts of this patch to interact, to exchange energy, and to reach a state of thermal equilibrium, a state of uniform temperature. Inflation then took this tiny, smooth, and causally connected region and stretched it to astronomical proportions in the blink of an eye. The uniformity was preserved, locked into the expanding fabric of space, creating the smooth, isotropic universe we see today. The second major puzzle solved by inflation is the flatness problem. General relativity tells us that the geometry of spacetime is determined by its total density of matter and energy. If this density is above a certain critical value, the universe will be closed, like the surface of a sphere, and will eventually collapse. If it is below the critical value, the universe will be open, like the surface of a saddle, and will expand forever. The flat universe of Euclidean geometry is a special knife-edge case, corresponding to a density that is exactly equal to the critical density. Our observations tell us that our universe is astonishingly, exquisitely flat. For this to be the case, the initial density of the universe at the time of the Big Bang would have had to be fine-tuned to a degree of precision that is almost beyond comprehension, about 1 part in 10 to the power of 60. This seems like an absurdly improbable coincidence. Inflation solves this problem in a natural and elegant way. Any initial curvature that the universe may have had, whether positive or negative, would have been stretched out and flattened by the immense exponential expansion. In the same way that inflating a small, wrinkled balloon to the size of the Earth would make its surface appear perfectly flat to an observer on it, inflation drives the geometry of the universe so close to perfect flatness that it is, for all practical purposes, indistinguishable from it. But inflation does more than just solve old problems. It makes a remarkable and testable prediction. The theory states that the tiny, unavoidable quantum fluctuations as in the inflaton field itself during the period of inflation would not have been smoothed out. Instead, they would have been stretched to macroscopic and even astronomical scales. These stretched-in-time quantum fluctuations would have become the seeds of cosmic structure, the tiny variations in density that, over billions of years, and would grow under the influence of gravity to become all the galaxies, the clusters of galaxies, and the vast cosmic web that we see today. The specific statistical properties of these primordial fluctuations, their near, but not perfect, scale invariants are a unique fingerprint of inflation, and they have been confirmed with stunning precision by our detailed maps of the cosmic microwave background. We are, in the most literal and profound sense, the children of quantum fluctuations. Our entire cosmic home, with all its grandeur and complexity, is a macroscopic fossil of the inherent uncertainty of the primordial quantum void, a void that was momentarily supercharged with an incredible inflationary energy. The theory of inflation, in its more modern and sophisticated forms, has led to a concept that is even more profound and mind-altering than the Big Bang itself: the idea of eternal inflation and the multiverse. The Russian-American cosmologist Andrei Linde, one of the key architects of modern inflationary theory, realized that the process of inflation, once started, may be very difficult to stop. In his model of chaotic inflation, the inflaton field is not a single uniform entity, but a field that has different random values in different regions of the primordial universe. In some regions, the field will quickly roll down its potential hill. Inflation will end, and a bubble universe like ours will be born in a hot Big Bang. But in other regions, quantum fluctuations can kick the field up the hill, causing inflation to continue, and even to become a self-reproducing eternal process. In this scenario, the end of inflation in our region was just a local event. The larger meta-universe, the inflationary sea, is still out there, expanding at an incredible rate and constantly spawning new bubble universes. The Big Bang was not a singular, unique event in the history of time. It is a common, ongoing process in the vast, eternal landscape of the multiverse. This is a vision of reality that is almost impossible to fully comprehend. Our entire observable universe, with its hundreds of billions of galaxies, is just one bubble in an infinite, bubbling foam of other universes. And these other universes may not be like our own. The decay of the inflaton field in each bubble could lead to different vacuum states, resulting in different fundamental particles, different forces of nature, different physical laws. There could be universes with 2 dimensions of space, or 10. Universes where gravity is a repulsive force, or where the speed of light is different. Most of these universes would be sterile, bizarre, and inhospitable wastelands, incapable of supporting any form of complexity or life. But in an infinite multiverse, even the most improbable events become not just possible, but inevitable. The existence of a universe like ours, with its specific and seemingly fine-tuned set of physical constants that allow for the formation of stars, planets, and conscious observers, is no longer a miracle to be explained. It becomes a simple selection effect. We find ourselves in a universe that is hospitable to life, For the same reason that we find ourselves living on a planet with liquid water and a breathable atmosphere, we could not exist to ask the question in any of the other, far more numerous, inhospitable environments. The multiverse, in this sense, provides a scientific, albeit untestable, explanation for the anthropic principle. The idea of eternal inflation and the multiverse is on the cutting edge of theoretical physics, and it is by no means universally accepted. Critics point out that it is, by its very nature, unobservable, and therefore may not be a truly scientific theory, but its proponents argue that it is a natural and almost unavoidable consequence of combining our best theories of cosmology and quantum field theory, and there may be ways to search for indirect circumstantial evidence. If our bubble universe had, in its distant past, collided with another bubble, it might have left a bruise on our cosmos, a specific circular pattern of temperature fluctuations in the cosmic microwave background. The search for such a cosmic scar is an active, if long shot, area of research. Whether the multiverse is a physical reality or a beautiful mathematical dream, the theory of inflation has fundamentally and irrevocably changed our view of our own origins. It has taken the Big Bang from a mysterious, unexplained singularity and placed it within a larger, dynamic, and potentially eternal cosmic context. It has shown us how the grand, macroscopic structure of our universe can be born from the subtle, microscopic quantum fluctuations of the void. And it has opened our minds to the breathtaking possibility that our entire cosmos is just a single, fleeting note in an infinite and eternal cosmic symphony. The concept of the Big Bang itself, the central event in our cosmic story, is one that is often shrouded in misconception. The popular image is that of a gigantic firework, a singular explosion happening at a specific point in a pre-existing empty space. But this picture is fundamentally wrong. The Big Bang was not an explosion in space. It was an explosion of space. It was not an event that happened at a particular location. It was an event that happened everywhere at once. To grasp this counterintuitive idea, the analogy of an expanding balloon is helpful. If you imagine our three-dimensional space as the two-dimensional surface of a balloon, and you draw a number of dots on this surface to represent galaxies, then as you inflate the balloon, you will see that every dot is moving away from every other dot. An observer on any given dot would see all the other dots receding from them, and the further away a dot is, the faster it would appear to be moving away. There is no center to this expansion on the surface of the balloon. The expansion is happening everywhere. The fabric of the balloon itself is stretching. In the same way, the expansion of the universe is a stretching of the fabric of space-time. Every point in our current universe, including the point where you are right now, was part of that initial, infinitely hot and dense state. The Big Bang happened right here and everywhere else. This is a direct consequence of Einstein's general theory of relativity, which describes space and time not as a static, absolute background, but as a dynamic, physical entity that can be bent, warped, and stretched by the presence of matter and energy. The Big Bang, then, is not a theory of the origin of the universe from nothing. It is a theory of the evolution of the universe from a very hot, dense, and rapidly expanding initial state. It does not, in its standard form, address the question of what caused the Big Bang, or what, if anything, came before it. Those are questions that lie beyond the domain of the theory, in the realm of quantum gravity and the speculative cosmologies we have discussed. The story that the Big Bang does tell is the story of the first 14 billion years of our universe's life, a story of cooling, of expansion, and of the gradual emergence of complexity from a state of primordial simplicity. In the first fractions of a second, the universe was an unimaginably hot and dense soup of fundamental particles, quarks, leptons, and the force-carrying bosons, a state known as a quark-gluon plasma. As the universe expanded and cooled, this plasma froze out. After about 1 microsecond, the quarks bound together to form the protons and neutrons that make up the nuclei of atoms. For the next few minutes, in a process known as Big Bang nucleosynthesis, These protons and neutrons fuse together to form the nuclei of the lightest elements, mostly hydrogen and helium, with trace amounts of lithium. The universe was still a hot, dense, and opaque plasma. The temperature was so high that electrons were not bound to the atomic nuclei. This sea of free electrons acted like a dense fog, constantly scattering photons of light, preventing them from traveling any significant distance. The universe was dark, not because there was no light, but because the light was trapped. This period lasted for about 380,000 years. Then, as the universe continued to expand and cool, it reached a critical temperature of about 3,000 Kelvin. At this point, the electrons had slowed down enough to be captured by the atomic nuclei, forming the first stable, neutral atoms. This event is known as recombination. Suddenly, the fog lifted. The universe became transparent to light. The photons that were present at that time were now free to travel unimpeded through space, and they have been traveling ever since. Their wavelengths stretched by the subsequent expansion of the universe from high-energy visible light into the cool, faint microwaves that we detect today. This is the cosmic microwave background, the oldest light in the universe, a beautiful, uniform glow that comes to us from all directions in the sky. It is a baby picture of our universe, a snapshot of the moment it first became transparent, a fossil that carries with it a wealth of information about the conditions of the early cosmos. The story of the Big Bang is a story of transformation, a story of how, from a state of almost perfect uniformity and simplicity, all the rich and complex structures we see today, the stars, the galaxies, the planets, and ourselves, were gradually born. It is a story that is written in the light of the distant stars, in the composition of the elements, and in the faint, ancient glow of the cosmic microwave background. It is our story. As our journey through the cosmos brings us closer to the present day, we encounter the universe's most profound and perplexing mystery, the existence of dark energy. This is not a subtle theoretical curiosity. It is the dominant component of our universe, making up roughly 68% of its total energy density. It is the invisible, silent force that is shaping the ultimate destiny of our cosmos, and we have almost no idea what it is. The discovery of dark energy in 1998 was a complete surprise. Two independent teams of astronomers, one led by Saul Perlmutter and the other by Brian Schmidt and Adam Rees, were using Type Ia supernovae as standard candles to measure the expansion rate of the universe at different times in its history. A Type Ia supernova is the thermonuclear explosion of a white dwarf star, and it always has the same intrinsic brightness, making it a perfect cosmic yardstick. The teams expected to find that the expansion of the universe was slowing down, as the mutual gravitational attraction of all the matter in the cosmos should be acting as a brake. To their astonishment, they found the exact opposite. The distant supernovae were dimmer than expected, which meant they were further away than they should have been if the expansion was slowing down. The expansion of the universe is accelerating. This groundbreaking discovery, which earned its leaders the 2011 Nobel Prize in Physics, implied the existence of a new, previously unknown form of energy with a strange and powerful property, a strong negative pressure that acts as a form of cosmic anti-gravity, pushing space-time apart. This is what we call dark energy. The simplest and most natural candidate for dark energy is the energy of the quantum vacuum itself, the zero-point energy we discussed earlier. In the context of Einstein's general relativity, a constant vacuum energy density would manifest as a cosmological constant, a term that Einstein himself had introduced into his equations in 1917, only to later retract it as his biggest blunder when Edwin Hubble discovered the universe was expanding. In a beautiful historical irony, modern cosmology has resurrected Einstein's blunder and made it the centerpiece of our standard cosmological model. A universe dominated by a cosmological constant has a strange and counterintuitive property. As space expands, the density of matter and radiation decreases, as they are spread out over a larger volume, but the density of vacuum energy remains constant. This means that as the universe gets bigger, the total amount of dark energy increases. It is as if new energy is being created from the expanding space itself. In the early universe, when the density of matter and radiation was very high, the effects of dark energy were negligible. But as the universe expanded and thinned out, dark energy gradually became the dominant component. It took over from gravity as the primary driver of cosmic evolution about 5 billion years ago, and it has been accelerating the expansion ever since. The problem, as we have seen, is the vacuum catastrophe. The theoretical value of the vacuum energy calculated from quantum field theory is an absurd 120 orders of magnitude larger than the observed value of dark energy. This colossal discrepancy has led many physicists to believe that the simple identification of dark energy with vacuum energy must be wrong. This has led to a host of alternative theories. Perhaps dark energy is not a constant, but is a dynamic entity, a new quantum field dubbed quintessence that is slowly rolling towards its minimum energy state. In this scenario, the rate of cosmic acceleration could change over time, leading to a different ultimate fate for the universe. Or perhaps our understanding of gravity is wrong. Maybe general relativity needs to be modified on cosmological scales. These modified gravity theories attempt to explain the accelerated expansion without invoking any new form of energy. They propose that gravity itself becomes repulsive on very large distances. Distinguishing between these different possibilities is one of the primary goals of modern cosmology. Observatories like the Euclid Space Telescope and the Vera C. Rubin Observatory are designed to map the distribution of galaxies and the history of cosmic expansion with unprecedented precision, which will allow us to measure the properties of dark energy and to test whether it has changed over time. The nature of dark energy is not just a question for physicists. It is a question that touches on the ultimate fate of our universe. A universe dominated by a constant dark energy is destined for a big freeze. A universe dominated by a phantom energy that grows stronger over time is destined for a big rip. And a universe where dark energy could one day decay or change its sign could be destined for a big crunch. We live in a universe whose destiny is being written by an invisible, mysterious, and powerful force. A force whose true nature remains one of the greatest and most profound challenges in all of science. The empty space that surrounds us is not empty at all. It is a dynamic, energetic, and powerful entity. A cosmic protagonist whose story we are only just beginning to understand. The idea that our universe might not be the only one, that it could be part of a vast, perhaps infinite, multiverse, is a concept that has migrated from the realms of science fiction and philosophy into the heart of modern theoretical physics. It is a breathtaking and humbling idea, one that, if true, would represent the final and most profound step in the Copernican revolution. The long historical process of decentering humanity from a privileged position in the cosmos. The concept of the multiverse is not a single, coherent theory, but rather a consequence of several of our most ambitious and successful physical theories. We have already encountered one of its most compelling sources, the theory of eternal cosmic inflation. In this picture, our universe is just one bubble that formed when a small patch of an eternally inflating meta-universe decayed into a lower energy state. Other bubbles are constantly forming, each potentially with different physical laws, constants, and even different numbers of dimensions. This creates a vast, level 2 multiverse of disconnected, parallel realities. Another powerful argument for the multiverse comes from the many worlds interpretation of quantum mechanics. As we discussed, this interpretation, first proposed by Hugh Everett, solves the measurement problem by positing that the wave function never collapses. Instead, every quantum measurement causes the universe to split into multiple branches, with each branch corresponding to one of the possible outcomes. This creates a level 3 multiverse, a constantly branching tree of parallel realities. In this multiverse, there are an infinite number of yous, each living out the consequences of a different quantum outcome. There is a version of you who is reading this, and a version of you who decided to go for a walk instead. Every possibility is realized somewhere in this vast quantum multiverse. A third and more straightforward type of multiverse is the level 1 multiverse. This is simply the idea that our observable universe, the region of space from which light has had time to reach us since the Big Bang, is just a small patch of a much larger and possibly infinite universe. If space is infinite, then in that infinite volume, every possible configuration of matter and energy must, by statistical necessity, repeat itself an infinite number of times. This means that somewhere out there, far beyond our cosmic horizon, there is another galaxy, another solar system, another Earth, and another you, an identical copy living out an identical life. And there are an infinite number of such copies. This is a staggering and deeply unsettling thought, one that challenges our sense of individuality and uniqueness. Finally, there is the most abstract and philosophical type of multiverse, the Level 4, or mathematical universe, proposed by physicist Max Tegmark. This is the idea that physical reality is, at its core, a mathematical structure. And since all consistent mathematical structures exist in a timeless, Platonic sense, then all possible mathematical structures exist as physical realities. Our universe is just one, particularly complex, mathematical structure, one that happens to have the right properties to allow for the emergence of self-aware substructures, like us, who can contemplate the mathematical nature of their own existence. The multiverse, in all its forms, provides a powerful, if controversial, framework for addressing the fine-tuning problem. The fact that the physical constants of our universe seem to be so exquisitely tuned to allow for the existence of life is no longer a miracle that requires a supernatural explanation. It is a simple selection effect. We find ourselves in a universe that is hospitable to life because it is the only kind of universe we could find ourselves in. We are the survivors of a cosmic lottery of unimaginable proportions. The primary criticism of all multiverse theories is that they are, by their very nature, untestable. We can never travel to another bubble universe or communicate with a parallel branch of the quantum wave function. This has led some to argue that the multiverse is not a scientific theory, but a metaphysical one. But its proponents argue that the theories from which the multiverse arises, like inflation and quantum mechanics, are themselves highly testable. If these theories continue to pass every experimental test we throw at them, then we may be forced to take their more bizarre consequences, like the multiverse, seriously, and there may be indirect, circumstantial ways to search for evidence. The cosmic bruise from a collision with another bubble universe is one such possibility. The search for a variation in the fundamental constants of nature across the sky is another. Whether the multiverse is a physical reality or not, the very fact that it is a serious topic of discussion among many of the world's leading physicists is a testament to how far our cosmic horizons have expanded. It is a concept that forces us to confront the true scale of reality, to question our most basic assumptions about our own uniqueness, and to embrace a vision of the cosmos that is infinitely richer, stranger, and more magnificent than we ever dared to imagine. As we gaze out into the cosmos, our vision is fundamentally limited. The night sky appears as a vast, dark dome, but this is an illusion. We are not looking out at a static, three-dimensional space. We are looking back in time. The light from the moon takes a little over a second to reach us, so we see it as it was a second ago. The light from the sun takes 8 minutes. The light from our nearest stellar neighbor, Proxima Centauri, takes over 4 years. And the light from the Andromeda Galaxy, our closest major galactic neighbor, has been traveling for 2.5 million years. When we look at the most distant galaxies visible in the James Webb Space Telescope, we are seeing them as they were over 13 billion years ago. When the universe was just a toddler, this intimate connection between distance and time defines our cosmic horizon. Because the universe has a finite age of approximately 13.8 billion years, and because light travels at a finite speed, there is a fundamental limit to how far we can see. The boundary of our observable universe is not a physical wall, but a temporal one. It is the distance from which light has had just enough time to reach us since the Big Bang. We can never, even in principle, see what lies beyond this horizon. The universe may be infinite, but our view of it is finite. The situation is made even more profound by the accelerating expansion of the universe. Not only is there a horizon that limits our view of the past, but there is also an event horizon that limits our view of the future, because space itself is expanding, and this expansion is accelerating. Distant galaxies are receding from us at ever-increasing speeds. there is a critical distance beyond which galaxies are receding from us faster than the speed of light. This does not violate Einstein's theory of relativity, as it is space itself that is expanding, not the galaxies moving through space. But it does mean that any light emitted by those galaxies after they cross this event horizon will never be able to reach us. They will be causally disconnected from our future. They will, in a sense, disappear from our universe. The night sky of the far future will be a profoundly lonely place. As more and more galaxies recede beyond our event horizon, the cosmic landscape will become increasingly empty. Eventually, only the members of our own gravitationally bound local group of galaxies will remain visible. A future civilization, looking up at the sky, might conclude that they live in a single island universe, forever unaware of the vast cosmic ocean that we are privileged to still be able to see. This concept of an event horizon, a one-way membrane that separates the observable from the unobservable, is most famously associated with black holes. A black hole is a region of space-time where gravity is so intense that nothing, not even light, can escape. Its event horizon is the point of no return. Any object or any information that crosses this boundary is seemingly lost to the outside universe forever. In the 1970s, Stephen Hawking revolutionized our understanding of black holes by showing that they are not completely black. Due to quantum effects at the event horizon, the constant creation and annihilation of virtual particle pairs from the quantum vacuum black holes should slowly emit a faint thermal radiation. This Hawking radiation causes the black hole to lose mass and, over immense timescales, to eventually evaporate completely. This brilliant discovery, which elegantly weaves together the principles of general relativity, quantum mechanics, and thermodynamics, also gave rise to one of the deepest paradoxes in modern physics, the black hole information paradox. According to the fundamental principles of quantum mechanics, information can never be destroyed. The total amount of information in a closed system must always be conserved. But if you throw an encyclopedia, with all its rich and complex information, into a black hole, that information seems to be lost forever behind the event horizon. And when the black hole evaporates, the Hawking radiation it emits appears to be purely thermal and random, containing no memory of the information that fell in. So, where did the information go? Is it truly destroyed, in violation of one of the most sacred principles of physics, or does it somehow escape, subtly encoded in the quantum correlations of the outgoing radiation? This paradox has been a major driver of research in theoretical physics for decades, and its resolution is thought to be a key step towards a full theory of quantum gravity. Recent theoretical work has suggested that the information is not lost, but is preserved on the event horizon itself, a concept related to the holographic principle, which posits that all the information in a three-dimensional volume of space can be encoded on its two-dimensional boundary. The existence of horizons, both cosmological and black hole, is a profound and humbling feature of our universe. It tells us that there are fundamental, built-in limits to our knowledge. There are parts of the cosmos and aspects of nature that may forever lie beyond the reach of our direct observation. But they are also a powerful spur to our theoretical imagination, forcing us to devise new and creative ways to understand the realities that are hidden from our view. They are a reminder that the universe is not a transparent, open book, but a deep and multi-layered mystery. A mystery whose most profound secrets are often hidden right at the very edge of what we can see. The grand narrative of our cosmos, as told by the standard Big Bang model, is a linear one. It is a story with a definite beginning, a long period of evolution, and a potential final end. But is this the only possible story? Could the universe be a more timeless, more cyclical entity, an eternal dance of creation and destruction, with no absolute beginning or end? This idea of a cyclic universe is one of the oldest and most enduring in human thought. It is found in the concept of the kalpas in Hindu cosmology, vast time cycles of cosmic creation, maintenance, and dissolution. It is present in the philosophy of the ancient Stoics, with their idea of a great year, at the end of which the universe is consumed by fire and then reborn. and it is a concept that has been given a new scientific life in some of the most advanced and speculative theories of modern cosmology. One of the most well-developed of these is the ekpyrotic or cyclic model, proposed by physicists Paul Steinhardt and Neil Turok. This model is rooted in the ideas of string theory and extra dimensions. It envisions our universe as a three-dimensional brane, or membrane, floating in a higher dimensional space, or bulk. There is another, parallel brane nearby. In this picture, the Big Bang is not the beginning of time, but is the result of a gentle, periodic collision between our brane and this other brane. Each collision releases a tremendous amount of energy, which is converted into the hot, dense matter and radiation of a new cosmic cycle. After the collision, the branes bounce apart, and our universe expands and cools, allowing for the formation of galaxies, stars, and planets. But this expansion is not destined to continue forever. A form of dark energy. In this model, a potential energy between the branes eventually causes the expansion to slow down and the branes to begin to move back towards each other, drawn together by a spring-like force. This leads, after a period of slow contraction, to another gentle collision, another Big Bang, and the beginning of a new cycle. Each of these cycles could last for 1 trillion years or more, an almost unimaginable timescale from a human perspective, but just a single beat in the eternal rhythm of the cosmos. This cyclic model has several attractive features. It elegantly solves the horizon and flatness problems of the standard Big Bang model without the need for a period of cosmic inflation. The smoothness of our universe is a result of the long period of slow contraction before the last bang, which had plenty of time to smooth out any irregularities. It also provides a natural explanation for dark energy as the force that drives the cycles. And most profoundly, it eliminates the need for an initial singularity, the point of infinite density and temperature where the laws of physics break down. In a cyclic universe, there is no absolute beginning. The universe has always existed and will always exist in an endless sequence of cosmic epochs. However, the cyclic model is not without its challenges. The physics of the brane collision, the bounce from a contracting phase to an expanding one, is incredibly complex and requires a full, and as yet unknown, theory of quantum gravity to be described accurately. And the model must also contend with the second law of thermodynamics. If entropy or disorder increases with each cycle, how can the universe return to the same low entropy state at the beginning of each new cycle? The proponents of the model argue that the vast expansion that occurs during each cycle so dilutes the entropy that it becomes negligible, effectively resetting the cosmic clock. Another related idea is the conformal cyclic cosmology (CCC) proposed by the eminent physicist Roger Penrose. In this model, the universe does not bounce, but expands forever. However, Penrose argues that in the very far future of our universe, after all the black holes have evaporated and only a cold, thin gas of photons and other massless particles remains, the universe loses its sense of scale. In this state, the infinitely large and cold future of our eon becomes mathematically equivalent, via a conformal transformation, to the hot, dense, low entropy state of a Big Bang for a new eon. The end of one universe becomes the beginning of the next. The cyclic models, in all their forms, offer a radically different vision of our cosmic story. They replace the linear, one-off narrative of the standard Big Bang with a more timeless, more eternal, and perhaps more philosophically satisfying picture of a universe that is constantly renewing and reinventing itself. While still a minority view among cosmologists, the idea of a cyclic universe is a powerful reminder that our current understanding is still provisional, and that the ultimate truth about our cosmic origins may be far stranger and far more beautiful than we can yet imagine. The apparent, exquisite fine-tuning of the fundamental constants of nature to allow for the existence of life is one of the most profound and philosophically charged mysteries in all of science. It is a puzzle that seems to hint at something deeper, something beyond the standard, materialistic worldview. Why is the strength of gravity just right to allow for long-lived stars? Why is the mass of the neutron just slightly heavier than the mass of the proton? a delicate balance that allows for the stability of atomic nuclei. Why is the cosmological constant so incredibly, exquisitely small, allowing for the formation of galaxies? This fine-tuning problem has led to the formulation of the anthropic principle, a controversial but powerful idea that attempts to explain this cosmic coincidence by invoking our own existence as observers. The weak anthropic principle is a relatively straightforward and almost tautological statement. It simply says that the conditions we observe in the universe must be compatible with the existence of observers. It is a form of selection bias. We find ourselves in a universe that is suitable for life because we could not have found ourselves in one that wasn't. It is a valid, but not particularly explanatory, principle. The strong anthropic principle, however, makes a much bolder and more metaphysical claim. It suggests that the universe is, in some sense, compelled to have properties that allow for the emergence of life and consciousness. This can be interpreted in several ways, from the theological, a divine designer, to the teleological, a cosmic purpose. The anthropic principle, in its weak form, finds a natural and scientific home in the context of the multiverse. If our universe is just one of a vast, perhaps infinite, ensemble of other universes, each with its own randomly assigned set of physical constants, then the fine-tuning problem dissolves. It is no longer a miracle that we find ourselves in a life-friendly universe. It is a statistical inevitability. We are simply living in one of the rare, habitable oases in a vast, sterile cosmic desert. This is a powerful and elegant explanation, but it relies on the existence of unobservable parallel realities. But is there a way to have a single, self-consistent universe without resorting to either a multiverse or a divine designer? This is the idea behind the bootstrap picture of the universe, a concept that has been a recurring dream in theoretical physics. The bootstrap hypothesis, in its most ambitious form, suggests that the universe is a completely self-consistent and unique whole. There is only one possible way for the universe to be: the values of the fundamental constants, the properties of the particles, the laws of physics themselves, are not accidental or random. They are all fixed by the requirement of overall mathematical and logical consistency. The universe, in a sense, pulls itself up by its own bootstraps. It is the way it is because it is the only way it could be. This is a vision of a universe that is not just described by mathematics, but is governed by a deep, underlying logical necessity. In this picture, there is no need for an anthropic principle to explain fine-tuning, because there is nothing to fine-tune. The constants have the values they do for the same reason that the ratio of a circle's circumference to its diameter is pi. It is a mathematical truth. The bootstrap dream was particularly popular in the 1960s in the context of the strong nuclear force, but it fell out of favor with the rise of the Standard Model, which seemed to have a number of arbitrary free parameters. However, the dream has not entirely died. The quest for a final, unified theory of everything, like string theory, is, in a sense, a quest for a bootstrap explanation. The hope is that a final theory will have no free parameters, that it will uniquely determine all the properties of our universe from a single, elegant set of principles. In the absence of such a final theory, the anthropic principle can be seen as a kind of poor man's bootstrap. It is a way of relating the properties of the universe to our own existence, a partial and existential form of self-consistency. When we observe a wild flower, we are also observing the universe that gave rise to it, a universe with the right chemistry, the right stellar evolution, the right physical laws. The organism and its universe are a self-consistent whole. The hope is that one day, our understanding will be so complete that when we observe a single electron, we will be able to deduce the properties of the entire universe from the requirement of self-consistency. We will find, as the poet William Blake wrote, a world in a grain of sand and a heaven in a wild flower. And the debate between the anthropic, multiverse picture and the bootstrap, unique universe picture is a debate about the very nature of physical law. Are the laws of nature contingent, accidental, and just one of a vast number of possibilities, or are they necessary, unique, and fixed by a deep, underlying logic. It is a debate about chance versus necessity at the most fundamental level of reality. And it is a debate that is far from being resolved. The quest to understand the universe inevitably leads us back to a profound and perplexing riddle, a riddle that lies at the very heart of the relationship between the knower and the known. It is the containment riddle where, in a universe, is the cosmologist who is studying that universe. This is not a trivial semantic puzzle. It is a deep, epistemological problem that challenges the very foundations of our scientific worldview. All other scientists can, to some extent, avoid this riddle. The biologist studies an organism, but she is not that organism. The geologist studies a rock, but he is not that rock. They can maintain a sense of objective distance, of an observer who is separate from the system being observed. But the cosmologist studies the entire universe, and she is undeniably a part of that universe. She is a product of the very cosmic evolution she seeks to understand. Her consciousness, her thoughts, her theories are all phenomena within the universe. How, then, can a part contain a picture of the whole that includes the part itself? This is a problem that has been recognized by thinkers for centuries. The philosopher and scientist Erwin Schrödinger, in his book Mind and Matter, pointed to this fundamental paradox. He noted that in order to create an objective, scientific picture of the world, we have, by necessity, excluded the subject of cognition from the domain of nature we seek to understand. We have stepped back and adopted the role of a non-concerned observer, and in doing so, we have created an objective world that does not, and cannot, contain the very consciousness that is doing the observing. The physical universe of our scientific theories contains our physical bodies, our brains, our neurons, but it does not contain our minds, our subjective experience, our awareness. The physical world of atoms and galaxies, governed by mathematical laws, is a brilliant and powerful construction, but it is a construction that is, by its very nature, incomplete. It is a map that does not contain the mapmaker. The containment riddle is a direct challenge to the philosophy of physicalism or materialism, the idea that life and mind are nothing more than the collective dance of atoms, that consciousness is fully contained within, and can be fully explained by, the physical universe. Those who hold this view often confuse the physical universe, which is a scientific model, a world picture, with the unknown universe, the totality of reality, which includes the mind that creates the picture. They mistake the mask for the face. The riddle forces us to confront the possibility that consciousness is not a phenomenon in the universe, but is, in some sense, co-extensive with it, or even primary to it. This is not to deny the immense success of the physical sciences. The physical universe is a powerful and useful model that allows us to understand how things work and to control our environment. But it is a model, an image, a story, and the storyteller, the image maker. The consciousness that weaves the facts and spins the ideas is not contained within the story. The answer to the containment riddle, then, is that we, the conscious, observing beings who create these universes of thought, do not live in our models. We live in the larger, unknown universe, the totality that includes both the physical world and the mind that knows it. Our scientific and philosophical models are our attempts to create a map of this territory, but the map can never be the territory itself. The physical universe contains the brain, but it is the mind that contains the physical universe. This is a subtle but profound shift in perspective. It suggests that an adequate cosmology, a true theory of everything, will not be complete until it can account for the existence of the cosmologist herself. It will require a new kind of science, a science that can bridge the gap between the third person, objective description of the physical world, and the first person, subjective reality of conscious experience. It is a challenge that has haunted philosophy in various guises for centuries. From the self-referential paradoxes of epistemology to the dizzying, bottomless chasm of self-awareness described by the Danish student in Paul Müller's famous tale. And it is a challenge that now, in the age of modern cosmology, stares the physicist directly in the face. We are not just in the universe is in us. And any final theory that fails to account for this fundamental, paradoxical, and beautiful truth will be, at best, a brilliant, but ultimately incomplete, picture of reality. The physical universe, as described by our scientific theories, is a world of matter, energy, and natural laws. But what, precisely, is a natural law? Are the principles that govern the evolution of life, for example, as fundamental as the laws that govern the motion of the planets? Since the time of Charles Darwin, the theory of evolution by natural selection has been the cornerstone of modern biology, and yet it has often been challenged as being unfounded speculation, a historical narrative that cannot be proven with the same rigor as a physical law like gravity. But this is a profound misunderstanding of the nature of science. The law of natural selection is as physical, as real, and as demonstrable as any other principle in science. The theory requires just three simple and observable components. First, an interbreeding population of organisms. Second, a source of variation among the members of that population, which we now know to be rooted in the random mutations of their genetic code. And third, a selective environment, a set of conditions that causes differential survival and reproduction. Those organisms whose variations happen to give them a slight advantage in a particular environment will be more likely to survive and to pass on their genes to the next generation. Over time, these advantageous traits will become more common in the population, and the species will change. It will adapt. It will evolve. This is not a speculation. It is a logical necessity. And we have overwhelming evidence for its effectiveness, not just in the fossil record, but in our everyday lives. The widespread use of antibiotics, for example, has created a powerful selective environment for bacteria. Those rare individual bacteria that happen to have a random mutation that confers resistance to an antibiotic will survive and reproduce, while their non-resistant cousins are wiped out. The result is the evolution of antibiotic-resistant superbugs, a direct and often dangerous demonstration of natural selection in action. The law of natural selection is a beautiful example of how simple, local, and random processes can, over time, give rise to immense complexity, order, and adaptation. It is a law that connects the microscopic world of genes to the macroscopic world of organisms and ecosystems. And it is a law that is deeply intertwined with the arrow of time. Evolution is a historical process, a one-way journey of increasing adaptation and complexity, a process that is only possible in a universe with a strong thermodynamic arrow of time. But is life itself, the very phenomenon that natural selection acts upon, something that is fully contained within the physical universe? This brings us back to the containment riddle. The biologists will tell us that life is a manifestation of complex, organized physical systems of cells and atoms. But this is a description of the how of life, not the what of life. It describes the physical vehicle, but not the subjective experience of being alive. The physical universe contains the physical representations of life, the wild flowers, the brains, the DNA. But does it contain the aliveness itself? The mystery of life, like the mystery of consciousness, seems to point to a reality that is not fully captured by our current physical models. It hints at a universe where the distinction between the living and the non-living, between the mental and the material, may not be as absolute as we assume. The law of natural selection is a physical law that operates on living systems, but the very existence of those living systems, with their strange and wonderful properties of self-organization, of metabolism, of awareness, remains one of the deepest and most beautiful mysteries of the cosmos. The boundaries of our universe, both in time and in space, pose some of the most profound and challenging questions in all of cosmology. We have spoken of the cosmic horizon, the limit of our observable universe. But what about the edges of time itself? A Big Bang universe, in its standard form, has a definite beginning, a time-like edge in the past. If this universe is destined to collapse back on itself in a big crunch, it will have two time-like edges, a beginning and an end. What is the nature of these cosmic boundaries? They are presumably not sharp, cliff-like edges, but are more likely to be regions where the very concepts of space and time, as we know them, break down. The orderly historical sequence of events that constitutes our classical, macroscopic world may dissolve into a chaotic, quantum, metrical foam at the beginning and the end of time. The truth is, we do not fully understand these time-like edges, perhaps because we do not fully understand the nature of time itself. Insofar as time is a physical dimension, a part of the physical universe, it seems logical to assume that it is contained within the universe and cannot extend outside of it. The question, what came before the Big Bang, is often dismissed as being meaningless, as before is a concept that requires the existence of time. But this is not necessarily the end of the story. There are ways in which we can talk sensibly about a before. If our universe is just one bubble in a larger, eternally inflating multiverse, then before our Big Bang, there was the inflating quantum vacuum of the meta-universe. If our universe is part of a cyclic model, then before our Big Bang, there was the contracting phase of a previous cosmic eon. And there is another, even more intriguing possibility, the idea of contained creation within a parent universe. Suppose that our universe is the offspring of another, pre-existing physical universe, reproduced either spontaneously through a quantum process, like the formation of a black hole, or perhaps, even more speculatively, deliberately, by a highly advanced intelligent life in the parent universe. In this scenario, we can meaningfully speak of what happened in the parent universe before the birth of our own. The physicist Joe Rosen has even shown that it is theoretically possible for such a system to be self-creating, a cosmic Ouroboros where Universe X creates Universe Y in its own time, and Universe Y in turn creates Universe X in its time. This distinguishes between contained creation, which is the emergence of a new thing at a specific time and place within a pre-existing space like the birth of a flower or a child, and uncontained creation, which is the timeless and placeless creation of the universe itself. The popular conception of the creation of the universe often mistakenly frames it as a contained creation, an event happening in a pre-existing void, which leads to the misguided question of what came before. A more sophisticated understanding sees the creation of the universe as an uncontained one, an event that brings time and space themselves into being. But the possibility of a parent universe reframes the question once again, suggesting that our universe's creation may have been a contained event within a larger, pre-existing reality. This is a concept that blurs the line between science, philosophy, and even theology. It is a testament to the fact that as our scientific understanding deepens, the questions we ask become more profound, more subtle, and more beautifully intertwined with the great, timeless mysteries of existence. The quest to build an adequate cosmology, a complete and satisfying picture of the universe, is inextricably linked to the quest to build an adequate philosophy of mind. The two are not separate endeavors, they are two sides of the same deep inquiry into the nature of reality. As the philosopher of science Edwin Burt wrote, a truly adequate cosmology will only be possible when we have a philosophy of mind that can satisfy both the behaviorist impulse to make the mind a material for experimental manipulation and exact measurement, and the idealist impulse to account for the startling difference between a universe without mind and a universe organized into a living, sensitive unity through mind. The human sciences, from psychology to sociology, currently face an impasse precisely because their central concept, the self, remains a deeply mysterious and transcendental entity, a concept that resists a purely materialistic explanation. At the roots of all our knowledge, from the most objective physics to the most subjective psychology, lies the containment riddle. This riddle, in its various guises, has haunted Western philosophy for centuries, and now it has come to haunt the foundations of physics itself. It is the riddle of the self-referential loop, of the system that tries to contain a complete description of itself. The physicist Leon Rosenfeld, a close collaborator of Niels Bohr, recounted how Bohr himself was deeply impressed by this problem, as it was expressed in Paul Müller's The Tale of a Danish Student. The student in the tale is tormented by epistemological paradoxes, by the fact that his mind divides itself into two persons, one who tries to fool the other, while a third, who is in fact the same as the other two, is filled with wonder at this confrontation. "I don't know which ego is the real one to stop at," the student laments. "For as soon as I stop at any of them, another ego stops at it. My head gets all in a whirl with dizziness as if I were peering down a bottomless chasm, and the end of my thinking is a horrible headache." This is the infinite regress of self-awareness, the mind that tries to observe itself, observing itself. It is the same infinite regress that confronts the painter who tries to paint a picture of his studio that includes himself painting the picture. And it is the same infinite regress that confronts the cosmologist who tries to create a physical model of the universe that includes the very consciousness that is creating the model. Erwin Schrödinger recognized this problem with profound clarity. "Without being aware of it," he wrote, "we exclude the subject of cognition from the domain of nature that we endeavor to understand. We step with our own person back into the part of an onlooker who does not belong to the world, which by this very process becomes an objective world." And this act of exclusion, this strategic stepping back, is what has allowed for the immense success of the objective, third-person perspective of science. But it is a success that has been achieved, as Schrödinger noted, at the high price of taking ourselves out of the picture. A complete and satisfying picture of the world, he argued, must somehow find a way to put the observer back in. The containment riddle is not just a puzzle for physicists and philosophers, it is a deep, existential reality that we all live with. We are both the subjects and the objects of our own experience. We are both the dreamer and the dream. And any final theory of reality that fails to embrace and account for this fundamental, paradoxical, and beautiful duality will be, at best, a partial and incomplete truth. The concept of a final theory, a single, complete, and consistent set of principles that would explain all the phenomena of the physical world, has been a powerful and enduring dream in the history of physics. The physicist Steven Weinberg, in his book, Dreams of a Final Theory, eloquently expressed this hope. Our present theories are of limited validity, still tentative and incomplete, but behind them now and then, we catch glimpses of a final theory, one that would be of unlimited validity and entirely satisfying in its completeness and consistency. String theory, with its potential to unify gravity and quantum mechanics, is often held up as the leading candidate for such a final theory. But is the quest for a final theory a realistic one, or is it a modern scientific version of an ancient religious quest for absolute truth against this modern dream of finality? We can contrast the medieval principle of learned ignorance, most famously articulated by the 15th century cardinal and philosopher Nicholas of Cusa. Cusa argued that the true path to wisdom lies not in the accumulation of knowledge, but in the growing awareness of our own ignorance. The more we know, the more we become aware of the vast, uncharted territory of what we do not know. This is not the simple, unlearned ignorance of the unaware, but a profound, learned ignorance, an enlightened state of humility and wonder. No man, Cusa wrote, can progress farther along the road to perfection than the point where he is found most knowing in the very ignorance that characterizes him. This is a perspective that resonates deeply with the current state of fundamental physics. Every major discovery, from relativity and quantum mechanics to dark matter and dark energy, has not led to a final, complete picture, but has opened up new, deeper, and more profound questions. The circle of our knowledge expands, but the circumference of our ignorance, the boundary with the unknown, grows with it. This suggests that the universe may be, in its very nature, inexhaustible. There may be no final theory, no bottom to the cosmic rabbit hole. Reality may be a series of nested, and perhaps infinite, layers of complexity and mystery. This is a humbling, but also deeply exciting, prospect. It means that the human adventure of scientific discovery will never be over. There will always be new horizons to explore, new puzzles to solve, new wonders to uncover. The quest for a final theory may be a necessary and powerful motivator for scientific progress, a guiding star that pulls us forward into the unknown. But perhaps the true wisdom lies not in the hope of one day arriving at a final destination, but in the journey itself, in the process of constantly expanding our knowledge and, in doing so, deepening our appreciation for the beautiful, infinite, and ultimately unknowable mystery of the cosmos. The choice between the dream of a final theory and the wisdom of learned ignorance is a choice between two different postures towards the universe, one of mastery and one of mystery, and perhaps a truly mature science, like a truly mature human being, will be one that can hold both. The very concept of space, which seems so simple and intuitive to us, has been the subject of a long and complex historical evolution, a journey that mirrors the development of our scientific and philosophical understanding of the world. From the heroic age of Greece until modern times, we can trace the development of two competing views: dressed space and undressed space. The idea of undressed space of a pure, empty void that exists in its own right, independent of the things it contains, was initially a radical and difficult abstraction. It was the view of the ancient Greek atomists, like Leucippus and Democritus, who proposed that reality consisted of nothing more than atoms moving in an infinite void. But for many, including the great philosopher Aristotle, this idea was nonsensical. A vacuum is nothing, he argued, and what is nothing does not exist. For Aristotle, space was always dressed, always filled with some kind of substance. He believed in a finite universe, with the Earth at its center, surrounded by a series of celestial spheres made of a fifth element, the ether. Beyond the outermost sphere of the fixed stars, there could be no space, because there was no matter, no ether, to fill it. This Aristotelian view of a dressed, finite space held sway for centuries. Medieval scholars, while grappling with the theological implications, eventually found a way to extend space beyond the sphere of the stars by inhabiting it with the omnipresence of God. But the idea of a true material vacuum remained a philosophical impossibility. In the 17th century, the French philosopher and scientist René Descartes also advocated for a form of dressed space. For him, the very definition of matter was extension, and so wherever there was space, there had to be matter. His universe was a plenum, a continuous, infinitely extended substance, with no possibility of a void. But the tide began to turn with the rise of experimental science. The invention of the air pump in the 17th century allowed scientists like Robert Boyle to create what appeared to be a vacuum in the laboratory, challenging the long-held Aristotelian and Cartesian views. This experimental evidence, combined with the immense theoretical success of Isaac Newton's physics, which was built on the concept of absolute, undressed space, led to the triumph of the Newtonian worldview. For the Newtonians, space was an infinite, eternal, and absolute container, a fixed stage upon which the drama of particles and forces played out. But the idea of a dressed space did not die. The discovery in the 19th century that light is an electromagnetic wave traveling at a finite speed raised a new question: what is the medium that is waving? Just as sound waves need a medium like air to travel, it was thought that light waves must need a medium to propagate through the vacuum of space. And so, physicists resurrected the idea of the ether, this time a luminiferous ether, a subtle, all-pervading substance that filled all of space and acted as the carrier for light. The advent of Einstein's special theory of relativity in 1905 finally did away with the need for an ether. Einstein showed that the speed of light is a universal constant, the same for all observers, and that the laws of electromagnetism do not require a special, privileged reference frame, which the ether would have provided. The undressed space of the atomists and Newton was reinstated, now unified with time, into the four-dimensional continuum of space-time. But the story does not end there. With Einstein's general theory of relativity in 1916, space-time was dressed once again, but in a new and far more profound way. Space-time was no longer a passive, static background, but a dynamic, physical entity, its geometry curved and warped by the presence of matter and energy. And as we have seen, the development of quantum field theory in the 20th century has given space-time its final and most mysterious dressing: the zero-point energy of the quantum vacuum, the seething, energetic sea of virtual particles that fills every corner of the cosmos. The history of our concept of space is a beautiful, dialectical dance between the abstract and the concrete, between the void and the plenum, between emptiness and fullness. And what we have arrived at today is a vision that, in a sense, unifies these two ancient ideas. The universe is, at its core, a quantum vacuum, an undressed space in that it is the fundamental ground of being. But this vacuum is not an empty nothingness. It is dressed with a rich, dynamic, and endlessly creative energetic structure, a structure that is the very source of all the matter, all the forces, and all the complexity we see in the world around us. The nature of time, even more so than space, is a subject that has perplexed and fascinated the human mind since the dawn of thought. What, then, is time? Asked the philosopher Saint Augustine in the 5th century. If no one asks me, I know what it is. If I wish to explain what it is to him who asks me, I do not know. These words still resonate with us today, capturing the deep, intuitive familiarity, and yet profound, conceptual elusiveness of time. We seem to experience time in a way that is fundamentally different from our experience of space. Space is the realm of the objective, the external, the world of things that we can see, touch, and measure with a meter stick. Time, on the other hand, seems to be the realm of the subjective, the internal, the world of our own, flowing stream of consciousness, of sensations, emotions, and ideas. And yet, modern physics has taken this subjective, flowing, and seemingly non-spatial experience of time and has, in a sense, spatialized it. It has stripped away many of the characteristics of the time we experience in our everyday lives, its flow, its transience, its division into a past, present, and future, and has made it akin to a dimension of space. Our physical world in the modern relativistic picture is a four-dimensional space-time continuum, a unified block of reality that contains all of space and all of time. This concept, which had its roots in the work of 19th century mathematicians and thinkers like Charles Hinton, was given its definitive form by Hermann Minkowski in the wake of Einstein's special theory of relativity. In a space-time diagram, the history of an object is represented by a world line, a line that traces its path through the four-dimensional continuum. A point on this diagram is an event, a specific location in space at a specific moment in time. The profound and unsettling consequence of this picture is that, in a very real sense, nothing ever happens in the space-time block. The entire history of the universe, past, present, and future, is laid out once and for all in a single, timeless, four-dimensional geometry. The restlessness of the world, its constant state of change and becoming, has been tamed, frozen into a static, eternal landscape. The philosopher William James dubbed this the block universe, a concept that does away with the very notion of a flowing now. In a tenseless, four-dimensional world, it is wrong to say that one event has happened, another is happening, and a third will happen. All events are simply there, at their specific coordinates in the space-time block. An object does not move along its world line from the past to the future. It simply exists at all the points along its world line simultaneously. The feeling of the flow of time, the sense of a moving now that separates a fixed past from an open future, is, in this view, a subjective illusion of our own consciousness. As the physicist Hermann Weyl wrote, "The objective world simply is. It does not happen, only to the gaze of my consciousness, crawling upward along the lifeline of my body. Does a section of this world come to life as a fleeting image in space which continually changes?" This is a powerful and elegant picture, but it is one that comes at a high price. It leaves us with a deep and seemingly unbridgeable gap between the timeless, static, and objective world of physics and the transient, flowing, and subjective world of our own lived experience. The problem of transience, of how to account for our powerful and undeniable experience of a moving now, is one that physicists tend to dismiss as a psychological or metaphysical issue, not a physical one. But as the philosopher Gerald Whitrow pointedly asked, how do we get the illusion of time's transience without presupposing transient time as its origin? How can a world in which nothing ever changes give rise to an experience of constant change? This is the paradox that lies at the heart of our modern understanding of time. If the now is moving up our world line At what speed is it moving? This question forces us to invoke a second dimension of time, and then a third, leading to the absurdity of an infinite, serial time. The spatialization of time, while a powerful and necessary tool for physics, seems to have left out the very essence of what time is for us, as conscious, living beings. The real problem, perhaps, is that we have tried to fit our rich, subjective experience of time into a purely objective, physical model. And in doing so, we have, as Schrödinger noted, taken ourselves out of the picture. A complete understanding of time may require a new kind of physics, a new kind of philosophy, one that can bridge the gap between the block universe and the flowing river, between the is of physics and the becomes of our own conscious experience. The puzzle of the arrow of time, the fact that the macroscopic world of our experience has a clear and unambiguous direction from past to future, is made even deeper by the fact that the fundamental laws of physics that govern the microscopic world are, for the most part, time reversible. The equations of motion for a single particle, the laws of electromagnetism, the Schrödinger equation of quantum mechanics, all of these work just as well for a movie played in reverse. And yet, the collective behavior of a large number of particles is clearly not time reversible. A mug of coffee on your desk will always cool down. It will never spontaneously heat up by drawing heat from the surrounding air. The flow of heat from hotter regions to cooler regions is a one-way street, a process governed by the second law of thermodynamics, the law of increasing entropy. This law provides the thermodynamic arrow of time. It seems that the arrow of time is an emergent phenomenon, something that arises from the collective, statistical behavior of many particles, but is not present in the laws that govern the individual particles themselves. It is like looking at a painting. If you look at a single dab of paint up close, you cannot tell which way is up. You have to stand back and look at the large-scale arrangement of many dabs of paint to see the picture and to know which way to hang it. In the same way, the arrow of time is not found in the microscopic details, but in the macroscopic patterns of the universe. We can visualize this in a space-time diagram. The world line of a single isolated particle has no inherent direction, but the world lines of the many particles that make up a hot cup of coffee are highly agitated. They are crinkled. And as time progresses, as we move up the diagram, this crinkledness, this agitation, spreads out to the neighboring, less agitated world lines of the surrounding air through collisions and other interactions. The system as a whole becomes more disordered, more crinkled on a larger scale. This process is not time reversible. If you were to turn the space-time diagram upside down, you would see agitation spontaneously concentrating from the cool air into the hot coffee, a clear violation of the second law. But this explanation just pushes the question back to the initial conditions of the universe. The second law only works because the universe started in a state of incredibly low entropy, a state of high order. The universe began with all its world lines in a very smooth, uncrinkled state, and the arrow of time is simply the story of the universe's long, slow, and inexorable journey towards a more crinkled, more disordered, and more probable state. Another, related, arrow of time is the electromagnetic or radiative arrow. The equations of electromagnetism are time reversible. They allow for both retarded solutions, where waves radiate outwards from a source into the future, and advanced solutions, where waves converge inwards onto a source from the past. In our universe, we only ever observe retarded waves. A light bulb emits light outwards. It never absorbs light inwards from all directions to become unlit. This is another fundamental asymmetry of our world, and it is also thought to be a consequence of the low entropy initial conditions of the universe. The cosmological arrow of time is the direction of the universe's expansion. The physicist Thomas Gold argued that this is the master arrow, that the future is, by definition, the direction in which the universe is expanding. This provides a clear directionality, but it raises the question of what would happen if the universe were to one day stop expanding and begin to contract. Would the arrow of time reverse? Would entropy start to decrease? Would people start to grow younger? This is a fascinating, if highly speculative, question. The current consensus is that the thermodynamic arrow of time would likely not reverse in a contracting universe. The processes that generate entropy are local and do not depend on the overall expansion or contraction of the cosmos. A contracting universe would likely continue its journey towards a state of higher entropy, culminating in a hot, dense, and highly disordered Big Crunch. All of these different arrows of time, the thermodynamic, the radiative, the cosmological, and the psychological arrow of our own memory, seem to point in the same direction in our universe. And they all seem to be rooted in the same deep and unexplained mystery, the incredibly special, low entropy state of the early universe. The arrow of time is not just a feature of physics, it is the very framework of our existence, the condition that makes life, memory, and causality possible. And the fact that this most fundamental feature of our reality is still not fully understood is a profound testament to the deep and enduring mysteries that lie at the heart of the cosmos. The basic parameters of our physical world, the fundamental constants of nature, seem, on the face of it, to be arbitrary and accidental. There is nothing in our current theories that explains why the speed of light has the value it does, or why the charge of the electron is what it is. They are numbers that we must measure experimentally and then plug into our equations. And yet, as we have seen, these numbers appear to be exquisitely fine-tuned to allow for the existence of a complex, life-bearing universe. This is the fine-tuning problem, and it presents us with a stark choice between two very different philosophical pictures of the cosmos. The first picture is the one offered by the anthropic principle in the context of a multiverse. In this view, our universe is just one of a vast, and possibly infinite, ensemble of other universes, each with its own, randomly assigned set of physical constants. The constants in our universe are accidental in that they are just one random draw from a vast lottery of possibilities. The reason we find ourselves in a universe with life-friendly constants is simply a matter of selection bias. We could not have found ourselves in any of the other, far more numerous, sterile universes. This is a powerful and scientifically respectable explanation, but it is one that many find to be philosophically unsatisfying, as it relies on the existence of an infinite number of unobservable realities and abandons the hope of a deeper, more fundamental explanation for the properties of our own. The second picture is the one offered by the bootstrap hypothesis. In this view, the universe is a single, unique, and completely self-consistent whole. There are no accidental or arbitrary features of a fundamental nature. The values of the constants, the properties of the particles, the very laws of physics themselves, are not random draws from a cosmic lottery, but are all fixed and uniquely determined by the requirement of overall mathematical and logical consistency. The universe is the way it is because it is the only way it could be. It pulls itself up by its own bootstraps. This is a much more aesthetically and philosophically appealing vision for many physicists. It is the dream of a final theory, a theory of everything that would have no free parameters, a theory from which all the properties of our universe could be derived from first principles. This was the dream that drove Einstein in his later years, and it is the dream that still motivates the search for a unified theory like string theory. In the bootstrap picture, the universe is not a random accident, but a mathematical necessity. In the absence of such a final bootstrap theory, the anthropic principle can be seen as a kind of makeshift or poor man's bootstrap. It is a way of establishing a relationship of self-consistency, not at the level of fundamental laws, but at the level of existence itself. It relates the properties of the universe to the existence of the organisms that observe it. When we observe a living organism, a wild flower, or a human being, we are also, implicitly, observing the universe that was capable of producing it, a universe with the right chemistry, the right stellar evolution, the right physical constants. The organism and its universe form a self-consistent, if partial, bootstrap loop. The ultimate hope of the bootstrap dream is that one day, our understanding will be so complete that we will be able to deduce the entire structure of the universe from the properties of a single, fundamental particle, like an electron. We will see, as the poet William Blake envisioned, a world in a grain of sand and a heaven in a wild flower. we will understand that the electron has the properties it does because it is part of a self-consistent whole, and that the universe has the properties it does because it is the only one that can contain a self-consistent electron. This is a vision of a universe that is not just a collection of contingent facts, but a deep, interconnected, and logically necessary unity. The choice between these two pictures, between the multiverse of chance and the bootstrap of necessity, is one of the central, unresolved tensions in modern fundamental physics. It is a choice that is not just about science, but about our deepest philosophical intuitions about the nature of reality. And it is a choice that may not be resolved until we have a final, complete theory of quantum gravity, a theory that can tell us whether our universe is a unique mathematical masterpiece, or just one beautiful, and very lucky, ticket in an infinite cosmic lottery. The quest to build a complete and satisfying picture of the universe, a cosmology that can account for all the phenomena of nature, is a journey that has led us to the very limits of our understanding, to the frontiers of space, of time, and of knowledge itself. We have traveled from the quantum foam of the primordial void to the eternal, self-reproducing landscape of the multiverse. We have explored the fiery crucible of the Big Bang, the strange, repulsive power of dark energy, and the deep, enduring mystery of the arrow of time. We have grappled with the paradoxes of quantum mechanics, the riddles of extra dimensions, and the profound philosophical implications of the anthropic principle. And in this grand intellectual adventure, we have been forced again and again to confront the limitations of our own human perspective. The containment riddle, the paradox of the observer who is part of the system being observed, is a stark and humbling reminder that any picture we create of the universe will be, by its very nature, incomplete. We are the mapmakers who are trying to draw a map of a territory that includes the mapmaker himself. This is a logical and epistemological puzzle that may never be fully resolved. It suggests that a final, objective, God's eye view of reality may be forever beyond our reach. The universe we know, the universe we study, is a participatory universe, a reality that is co-created in the dialogue between the cosmos and the consciousness that seeks to understand it. This does not mean that science is a purely subjective enterprise. The physical universe, as described by our scientific theories, is a powerful and remarkably successful model. It has allowed us to understand the workings of nature with incredible precision, to control our environment, and to create the technologies that have transformed our world. But it is a model, a map, a story. And it is a story that is, at present, profoundly incomplete. It has a gaping hole at its very center, the mystery of life and mind. Our physical theories can describe the dance of the atoms that make up a brain, but they cannot explain the subjective experience of consciousness that arises from that dance. They can describe the chemical processes of a living cell, but they cannot capture the emergent, holistic property of aliveness itself. The person who persistently asks, "Where is life in the physical world?" is passed from biologist to psychologist to physicist, each discipline admitting, in its own way, the limits of its own perspective. The buck, as the saying goes, stops with the cosmologist, because the cosmologist is the one who claims to study the whole thing. But the cosmologist, too, must confess a deep and profound ignorance. A truly adequate cosmology, as the philosopher Edwin Burt noted, will not be possible until we have an adequate philosophy of mind, one that can do justice to both the physical and the mental, the objective and the subjective, the outer and the inner aspects of our reality. The journey to understand the origin of the universe is, in the end, a journey to understand ourselves. We are not separate from the cosmos. We are a part of it. We are the universe's way of becoming aware of itself. The atoms in our bodies were forged in the fiery hearts of long-dead stars. The consciousness that is listening to these words is a product of a 14 billion year-long cosmic evolutionary process. And the questions we ask about the universe, its origin, its nature, its destiny are the universe's own questions, asked through us. This is a vision of our place in the cosmos that is both profoundly humbling and deeply empowering. It is humbling because it reminds us of our finitude, of the vastness of our ignorance, of the deep and enduring mysteries that will likely always lie beyond our grasp. But it is also empowering because it places us, as conscious, questioning beings, at the very heart of the cosmic story. We are not just insignificant specks of dust in a cold, meaningless void. We are the meaning makers, the storytellers, the observers through whom the universe comes to know and to wonder at its own magnificent existence. And as you lie on the threshold of sleep, as your own individual consciousness prepares to dissolve into the vast, mysterious, and creative ocean of the unconscious, you can feel a sense of participation in this grand, cosmic adventure. The journey is far from over. The greatest discoveries, the most profound insights, may still lie ahead. But the quest itself, the shared human endeavor to understand our cosmic home, is a journey that gives our fleeting lives a meaning and a dignity that can rival the stars themselves.
Under a tapestry of unfamiliar constellations, a red twilight settles across an ocean world. Two moons, arched in slender crescents, cast faint, rust-hued reflections on the slow-moving tide. The sun, a long-burning ember in the sky for weeks, has finally dipped below the horizon, and with it vanishes the oppressive breath of summer. Now, the world is lit by a sky choked with tens of thousands of stars. Above the curved silhouettes of the twin moons, a single point of light flares brighter than all others. A celebration erupts across continents. These people know what this is. For them, this is tradition. This is a guest star, a supernova, yes, but dressed in older language. And yet while crowds gather in joy, a single observer watches in horror. Satellites report a catastrophic dip in atmospheric ozone. The star is not just bright, it is close, too close. Within a week, the sky will turn from guardian to executioner. Had such an event struck Earth, the result would be the same mass extinction. But this is not Earth. This is a world that bloomed and burned out when our universe was young and restless. Galaxies were still embryonic. Starbirth exploded across cosmic neighborhoods, and death came just as swiftly, with each detonation of stellar grandeur bathing space in radiation and violence. These were the nursery days of worlds, and the cosmos was both generous and brutal. What kind of planets emerged in those early fires? What strange cradles of matter gave shelter to the first sparks of life, if life dared to arise at all? Not long ago, imagining the existence of worlds beyond our solar system was pure speculation. That other stars might host planets like our own seemed logical, but unprovable. Today, not only do we know exoplanets exist, we know they are everywhere. Thousands have been confirmed, tens of thousands are suspected, and still, we have only scraped the faintest frost from the tip of the iceberg. Many of these planets defy our imagination. Some are vast gas giants, clinging to their stars at blistering distances, their atmospheres whipped by winds that carry molten glass. Others are giants darker than coal, absorbing nearly all light. There are ringed behemoths with halos spanning hundreds of millions of kilometers. There are scorched earths that glow from tidal agony, and frigid wanderers cast adrift in the darkness between stars. And somewhere among them may be the quiet ones, the blue marbles tucked into gentle orbits, wrapped in atmospheres thick with nitrogen, traced with water vapor and carbon dioxide. These are the ones that might breathe. To find them, astronomers devised clever methods. They measured the trembling of stars, tugged by the invisible pull of planets. They watched for dimming starlight as planets passed in front of their suns. They listened for the rhythm of pulses from dead stars whose consistency revealed the gravitational fingerprint of orbiting bodies. Even from hundreds or thousands of light years away, they hunted the specters of alien skies and the contaminated light filtering through thin planetary atmospheres. Their discoveries painted a cosmic gallery more diverse than anything we had imagined. In some systems, planets dance in tight synchrony, so close their days are measured in hours. In others, twin suns rise and set in surreal choreography. Rocky worlds orbit dwarfs, giants, and even the burned-out cores of long-dead stars. Some have rings wider than the Earth-Moon distance. Some are little more than exposed cores, their outer layers long since torn away. One of the earliest detections came from a pulsar, a dead star spinning with unimaginable speed, sweeping its surroundings with radiation. There, two worlds clung in tight orbits. Later, we found gas giants hugging their stars at impossible distances, far closer than Mercury sits from our sun. These hot Jupiters, bloated and strange, were not what we expected, but they were easy to find. Their very improbability made them visible. Eventually, we found smaller planets, some not much larger than Earth, some orbiting within the so-called habitable zones of their stars, worlds like Kepler 186f and K2 18b, where hints of water and complex molecules in the atmosphere make astronomers lean closer to their telescopes. With each detection, we come closer to answering a question that has haunted us since the beginning. Are we alone? But even as we look forward with new missions, with the James Webb already reshaping what we thought we knew, and the Habitable Worlds Observatory preparing for a launch that is still decades away, we also look backward. How early did planets form? How fast did the cosmos learn to build homes for life? The universe wasted no time. The first stars formed within a few 100 million years after the Big Bang. Born from pure hydrogen and helium, they lived briefly and died explosively. In their deaths, they forged carbon, oxygen, silicon, the stuff of planets. The next generation of stars inherited this enriched matter, and with it, the ability to form rocky worlds. One of the oldest known stars, TOI 561, is over 10 billion years old. Around it, astronomers found a super-Earth, not gas, not vapor, but rock. Somehow, in a cosmos still young and under construction, a planet of solid matter took shape. And what of life? The record on Earth is suggestive. Life began as soon as the conditions allowed. Perhaps that is universal. Perhaps the moment a planet is stable, the moment water pools, chemistry stirs to life. If that is true, then there may have been civilizations' entire histories rising and falling before our solar system even existed. Of course, survival is another matter. The early universe was not kind. Supernovae were common, their death shouts loud and lethal. Galaxies collided more often. Radiation bathed entire regions. But life, if it had shelter, might persist. On moons buried under ice, in oceans shielded by thick atmospheres, in caves lit by the slow churn of geothermal warmth. The first exoplanets may have orbited dead stars. Some may have been born again from the debris of supernovae. Planets can survive where stars cannot. And life, stubborn and secretive, may have found ways to persist. Today we know of planets that orbit twin suns, planets with diamond crusts, planets of endless storm, of lava, of ice, of hydrogen oceans, and super-Earths with thick atmospheres where pressure might allow strange chemistry to unfold. We know of rogue planets that wander the galaxy alone. And still, we are only at the beginning. Even in our own solar system, we have yet to exhaust all possibilities. The Kuiper Belt, that distant ring of icy remnants, is home to ancient relics like Arakoth, small, cold, and unassuming. It remembers the solar system's birth. There may be billions more like it, the foundational debris from which planets are made. Worlds can begin as dust and ice, growing slowly or not at all, lingering at the edges of starlight. If such objects formed early and survived the fires of stellar adolescence, they might persist for eons, untouched and unread, like forgotten pages in a cosmic archive. And if one of those pages held life, if one of those icy worlds or buried oceans gave rise to consciousness, then perhaps they looked back. Perhaps they saw us, a pale blue dot circling an ordinary star, lost in a spiral arm. And perhaps they wondered if they, too, were alone. But we are here now, looking out, reaching, listening, and with every new discovery, we find that the universe is more generous than we dared hope, that planets are common, that diversity is the rule, not the exception, that life, if it can arise, might have had countless chances. The stars are full of secrets, and somewhere out there, beneath another sky of moons and fire, a new guest star may already be rising. The stars had begun to rise again over the quiet plains of a distant world. Its surface, pitted and ancient, bore the scars of countless impacts. Above, the twin suns had long since dipped below the horizon, and a sharp chill settled in their absence. Yet the sky was anything but still. Constellations stretched across the heavens in impossible patterns, lit not just by the ordinary stars of their galaxy, but by something else, a guest star, radiant and terrible, still pulsing with the residue of a titanic death. The people of this world had celebrated its arrival with fireworks and song, yet some had known the danger. Some had read the warnings, and when the sky dimmed not because of the night, but because of the ruin spreading through their atmosphere, they understood too late. We are not so different. We too live under a sky that holds both wonder and threat. We too reach out, seeking signs that we are not alone, that others have survived, even thrived. And in that search, we have begun to find them, not life, not yet, but the homes where life could dwell. The first signs came not from places of comfort, but from the strangest of sources. A pulsar, dense as an atom and spinning with the rage of a collapsed sun, pulsed its radiation with mechanical precision, and then a stutter, a hesitation in its rhythm. That hesitation revealed the gravitational whisper of planets, unseen but undeniable. They were dead worlds orbiting a dead star, but they were worlds nonetheless. It was the beginning. Then came the hot Jupiters, giants too close to their stars, their atmospheres churning, their orbits defying logic. They were not like anything in our solar system, and that made them all the more visible. Then came the others, worlds dark as ink, their surfaces drinking in all light. Worlds of glass storms and cobalt skies, worlds that glowed from within. Torn by tidal violence, the catalog grew. For a time, it seemed as though the universe favored the strange, the wild, the inhospitable. But the tools sharpened, and the surveys deepened, and we found more. Super-Earths, mini-Neptunes, worlds with gentle orbits and familiar sizes, worlds where water might pool and air might linger. We found systems of harmony and chaos, planets circling binary stars, moons the size of Mars, rings wider than the sun. And still we only saw the beginning. The techniques improved. We stared at stars, waiting for a tiny eclipse. We listened for the tremble in starlight. We parsed spectra, finding fingerprints of molecules in the atmospheres of alien skies. Each method, refined, revealed more. Kepler stared at a patch of sky and found thousands. Tess widened the gaze and found thousands more. And with each new telescope, each new mission, the flood continued. Not every discovery was dramatic. Some were quiet, some were strange, some were beautiful. A world called Phoenix clung to its atmosphere against all odds, orbiting a dying star. Another, Kepler 16b, circled two suns in an echo of a galaxy far, far away. One planet shone deep blue, not from oceans, but from scattering particles in a deadly wind. Another vanished into blackness, reflecting less light than charcoal. But the true marvel came when we began to understand what they might mean. That planets form not only in comfort, but in chaos. That they arise around stars old and new, rich and poor in metals. That they orbit pulsars and giants, dwarfs and dead remnants. That they can form anew from the ashes of supernovae. That where there is dust and time, there are worlds. The process is ancient. Dust becomes rock. Rock becomes planetesimal. Gravity draws them together. Heat sculpts them. Chemistry begins. It takes time, but not always as much as we thought. Around one of the oldest stars in our galaxy, TOI 561, we found a rocky world. The star is 10 billion years old. The planet must be nearly as ancient. Perhaps it had oceans. Perhaps it had life. Perhaps it still does. And what of life? We know only one world where life arose, but it did so quickly. It did so with stubbornness. If that pattern holds, then life too may be common. It may be old. It may be watching. Around a giant planet named Methuselah, orbiting within a globular cluster of stars, we found a world nearly 13 billion years in age. We do not know how it formed. We do not know if it lives, but we know it is ancient. And where there is age, there is time. And where there is time, there is possibility. The first planets may have known only fire and silence, but some endured. Some became cradles, and some, perhaps, became home. If life could survive the chaos of early galaxies, the fury of supernovae, the collapse of stars, then perhaps it is more common than we dared hope. We stand at the edge of that knowing. We send our eyes into space. We craft mirrors that will unfold in orbit, hunting for the signs we seek: water, oxygen, methane, disequilibrium. Not just the ingredients of life, but the breath of life itself. The telescopes to come will see further, sharper, deeper. They will not merely count planets, they will study them. They will reveal their atmospheres, their climates, their seasons. They will find, perhaps, the pale blue dots of other civilizations, or perhaps they will find the red deserts of a planet that tried and failed, or perhaps just silence. But even silence tells a story. It tells us where not to look. It tells us what paths not to follow. It narrows the possibilities. It sharpens our search. And so we continue, from the death throes of a nearby star to the icy memory of distant Arakoth, from the strangled orbit of a glowing Earth to the grandeur of ringed super Saturns. We chart a cosmos that teems with worlds. Many are harsh, some are beautiful, a few may be kind. But all of them matter. Each world is a chapter in a story that spans galaxies and epochs, and we, fragile and hopeful, are learning to read it. The skies are not empty. They never were. They are full of destinations, full of questions, full of homes, and maybe, just maybe, full of neighbors. In a star system 66 light-years from Earth, a small rocky planet orbits so tightly that it completes a full revolution in barely more than 2 days, scorched by its nearby sun and stretched by the violent gravitational tug-of-war of neighboring gas giants. This world glows like an ember. It is not volcanic. It is not molten. It is incandescent, lit not from within, but by the torment of tidal forces squeezing and twisting its rocky flesh. The heat generated from this ceaseless punishment pushes its surface temperature above 2000 Kelvin, igniting the very crust into radiance. From a distance, it might look like a slow-motion spark, drifting through a solar ballet that threatens to tear it apart. We have never seen its surface directly. We have never watched its glow, but its existence, its temperature, its tormented orbit, we know these from whispers in the light, from the slightest shifts in spectral lines, from dips in a star's brightness measured over months. It is extraordinary what we can learn from a single line on a graph. This planet is not alone. Thousands of such exoplanets crowd the expanding library of worlds, most known to us only as squiggles of light and shadow. But in those squiggles lies enough detail to paint rough portraits, to tell stories of fire and ice, of oceans lost and atmospheres born, of violence, silence, and survival. And behind these stories are spectrums, the coded light fingerprints of alien atmospheres, light filtered through distant air, tinged with the breath of exotic molecules. Astronomers work backward from these impressions. They take the physics of light, the chemistry of gases, the mathematics of planetary motion, and apply them like sculpting tools to shape the outlines of alien worlds. A hint of methane here suggests a reducing atmosphere. A dash of carbon dioxide there hints at volcanic activity. When water vapor appears, the signal is dim but electric with possibility. We do not need to visit these planets to begin understanding them. Some of the greatest surprises have come not from confirming what we expected, but from confronting what we never imagined. Take the hot Jupiters, gas giants, found orbiting so close to their stars that they ought not exist. These are worlds so close to their parent stars that their upper atmospheres puff outwards under the sheer assault of radiation, becoming distended, vulnerable to evaporation. In extreme cases, The atmosphere is so bloated that it forms a comet-like tail, dragged away from the planet in a constant hemorrhage of gas. The mystery of how such giants arrive at their unnatural proximity sparked decades of research. They could not have formed so near to their stars any nearby hydrogen, and helium would have long since evaporated in the early violent youth of stellar ignition. So they must have formed farther out and then migrated inward, a planetary journey that may have destroyed siblings, triggered collisions, or even changed the orbital layout of entire systems. These giant planets, once considered rare anomalies, are now a common feature of exoplanet catalogs. Their oddity helped make them easy to find. Their size and tight orbits yield strong signals. But as techniques improved, smaller worlds began to appear, worlds that might be rocky, that might cling to water, that might, in rare cases, nurture life. Around small red dwarf stars, the dim embers of the galaxy, many of these planets were discovered. These stars are faint, long-lived, and temperamental. Their planets, often tidally locked, face their star with eternal day on one side and endless night on the other. Still, many orbit in the so-called habitable zone, the region where liquid water might persist. Life, as we know it, depends on such water. And so the question becomes, can such worlds bridge that eternal twilight and give birth to something enduring? Of the methods astronomers use to find exoplanets, the transit technique reigns supreme. When a planet crosses in front of its star, even from our far-flung vantage, it causes a minute but measurable dip in light. The shape of that dip, the timing, the duration all tell us something. We can infer the planet's size, its orbital period, sometimes even the presence of clouds in its atmosphere. When combined with radial velocity measurements, which reveal how much a star wobbles due to the planet's gravitational tug, we can estimate a planet's mass. With both size and mass in hand, we get density, and from density, a guess stone or gas, iron or ice. Beyond Kepler, the transiting exoplanet, Survey Satellite, or TESS, has taken up the mantle. It scans swaths of sky, hunting for those subtle flickers. Thousands of candidate worlds have emerged from its gaze, some confirmed, many still waiting. Among them is a world nicknamed Phoenix, orbiting a star so massive it should have boiled the planet dry. Yet Phoenix retains an atmosphere, hugging it close like a secret. For now, models suggest it may be living on borrowed time. And soon, the next generation will arrive. The Nancy Grace Roman Space Telescope, launching in the near future, will use microlensing, a technique that relies on gravity itself to reveal planets. When a star passes in front of another star, the gravity of the foreground star can bend and focus the background light. And if a planet happens to be orbiting the foreground star, its presence can leave a detectable fingerprint in the light. This method is unbiased toward size or orbit, opening a window to a vast new population of hidden worlds. But even beyond finding planets, we aim to know them, to read their air, to see their surfaces. The James Webb Space Telescope has already begun this work. With its infrared gaze, it has peered into the clouds of gas giants, read the atmospheres of sub-Neptunes, and caught the faint exhalations of worlds dozens of light years away. Methane, carbon dioxide, water vapor, all have been spotted. In the spectrum of K2-18b, an intriguing mix of chemicals emerges, whispering of processes that, on Earth, would require life. None of this guarantees that life exists there. Abiotic chemistry can mimic biology in deceptive ways, but what matters is not certainty, it is possibility. For every such planet we detect, for every hint of habitability, the stage widens, the play becomes grander, the universe becomes a canvas that might include life again and again in endless variations. We live in an age where light alone tells us of distant worlds. We listen for silence and find symphonies. We peer into the dark and find it filled with echoes. Somewhere out there, beneath thick clouds or icy crusts, the conditions that cradle life may have arisen. And in knowing that, we begin to prepare, not just to discover more, but to ask deeper questions. What makes a world alive? What keeps it breathing? And how many candles has the universe lit, only to let them burn unseen? The cosmos is not silent. It speaks in spectra, pulses, and gravities. And with every passing year, we learn a few more syllables of its language. Among the stars, the stories of planets continue to unfold, stories of agony, survival, migration, and balance, each one a chapter in a cosmic novel still being written, and somewhere in those stories may lie the preface to our own. Somewhere in the galactic heart of a spiral arm, a new world begins to take shape. A star is born from a collapse of dust and gas, its ignition the signal for a planet-forming dance to begin. Around this star, a disk flattens and spins, littered with the debris of creation. Within this chaotic swirl, dust clings to dust, grains coalesce, and the earliest seeds of planets take root. This is how it has always begun. And across the galaxy, it is happening again and again. We know this not from direct observation, but from scattered glimpses. We have seen stars still wrapped in their disks, illuminated from within by fusion barely begun. We have seen young systems with arcs and gaps carved by infant planets. These fleeting moments, like frames in a cosmic film reel, are all we need to stitch together the tale of planetary birth. The process unfolds slowly by human standards, but swiftly on cosmic scales. Within a few million years, what was once dust becomes a planetesimal. Within tens of millions, these grow into full-fledged worlds. The location within the protoplanetary disk matters. Close to the star, the heat drives away volatiles, leaving behind iron and rock. Farther out, beyond the snow line, ice and gas can accumulate. Here, giants are born, and between these two extremes lies the fertile band we call the habitable zone. But this is not a static range. Stars evolve, orbits shift. What is temperate today may be seared tomorrow. And yet, despite all this, the universe seems insistent on building planets. Even in environments we once thought hostile to their formation, planets appear around old, metal-poor stars like Teofard 61, around binary systems, around the remnants of supernovae. Even around the cosmic undead pulsars and white dwarfs worlds have been found. This resilience suggests that once the universe had the raw materials, planets became inevitable. Stars light the stage, but planets are the actors, and some of those actors may carry life. What we have begun to understand, slowly and with caution, is that diversity is the law of exoplanets. For every Earth-like world we seek, a dozen others surprise us, some with compositions beyond prediction, others with orbits that defy classical mechanics. Take the circumbinary planets, orbiting two suns in a delicate, synchronized ellipse, or rogue planets, flung from their systems to wander lightless and alone. These drifters, cold and forgotten, may yet retain internal heat, with a thick enough blanket of atmosphere or an insulating ocean beneath an icy shell. Even these could harbor microbial life. Planetary mass, orbit, and composition are not the only keys. Time is a factor. Planets need time to cool, time to stabilize, time to host chemistry. Around stars that live for billions of years, time is abundant. Red dwarfs, for all their flaring rage, offer longevity. Some will burn for 100 billion years or more, long after the sun has expired. Their planets, if they survive the early tantrums of youth, may be the longest-standing homes for life in the universe. And then there are the atmospheres, thin or thick, scorching or frigid, transparent or opaque. Atmospheres reveal as much as they obscure. They are both veil and window. In them, we search for biosignatures, chemical imbalances that, on Earth, would suggest biology. Oxygen paired with methane, carbon dioxide alongside water vapor. These are fragile combinations. On Earth, they persist only because life continually replenishes them. If we find them elsewhere, we cannot assume life, but we cannot ignore the hint. Already, James Webb has turned its eye to promising targets. K2-18b stands out a world, neither Earth nor Neptune, wrapped in a dense atmosphere, showing whispers of methane and carbon-bearing compounds. It is a candidate, not a confirmation, but even one candidate is cause for hope. We are now at the threshold where planets are not only known, but characterized. This transition marks a new era. The age of exoplanet discovery is becoming the age of exoplanet exploration. And with the upcoming Habitable Worlds Observatory, we hope to go further, to photograph a pale dot orbiting a sun-like star, to separate its light, to read its air, to see if it breathes. This telescope, still on the drawing board, will unfold in orbit like a mechanical flower. Its mirrors will be vast, its vision sharp enough to find the fingerprints of life across the void. But such ambitions demand patience. The design, testing, construction, and launch span decades. The data, once it arrives, must be parsed carefully, compared, modeled, and retested. False positives abound. Confirmation is slow, yet there is no rush. The universe is old. The planets have waited. And while we wait, we imagine, we model molten exoplanets, oceans of lava under skies of silicate rain. We simulate super-Earths with crushing gravity and air like syrup. We dream of water worlds with no land at all, just endless sea under clouds that never break. We speculate about diamond planets, forged in high-pressure crucibles. Each possibility is a thought experiment, a boundary pushed. This is the scientific imagination at its best, grounded in data, but unafraid to dream. And every new telescope, every new detection, turns dream into question, and question into experiment. What we imagined yesterday we might observe tomorrow. So much of what we now accept as common gas giants in tight orbits, planets around red dwarfs, moons with subsurface oceans, was once thought improbable or impossible. The lesson is clear: expect surprise. The universe is under no obligation to conform to our intuition. And so we return to the skies, to the data, to the spectra, to the equations. Each planet is a story, and every story begins with a few points of light. With time, those points become portraits, and some portraits begin to smile back. The stars do not hide their children. We have only just learned how to look. The first light in the universe did not come from planets. It did not come from life. It emerged from the collapse of primordial hydrogen, from the ignition of the first stars in a cosmos, barely a few 100 million years old. These stars were immense, short-lived titans that lived fast and died violently, spewing heavy elements into their surroundings. In death, they gave the cosmos the ingredients it needed to begin building the second generation of stars and, eventually, the first planets. From that ancient starlight came the foundations for all worlds. The dust scattered by early supernovae seeded the galaxies with carbon, silicon, oxygen, and iron, the scaffolding of rock and metal. Yet those elements were sparse, and the early universe remained hostile. Frequent collisions between forming galaxies, bursts of radiation from quasars and gamma-ray bursts, and the chaotic dance of gravitational interactions made it a turbulent cradle. And still, the universe persisted. Planets formed, moons accreted, gas giants migrated, and some small rocky worlds settled into orbits just right for warmth and water. The first truly ancient planets likely formed when the universe was less than 1 billion years old. These were not necessarily Earth-like, but they were solid, real places, perhaps scorched, perhaps frozen, perhaps gaseous. They orbited metal-poor stars that had nonetheless acquired just enough building blocks to birth something more than light. Some of these worlds may have endured for billions of years. Some may still circle their ancient suns, quiet and unchanged, since a time before galaxies had even settled into their modern spirals. Among these elders is Methuselah, a gas giant orbiting a pulsar in the globular cluster M4. It is over 12 billion years old. Its origin story is tangled, formed around a sun-like star, captured by a neutron star, its system reshaped by stellar collisions and gravitational entanglements. Methuselah is a survivor, and if it formed moons in its youth, some of them may have harbored oceans beneath thick ice, sheltered from radiation. They could have given life a fighting chance when the rest of the galaxy was still an inferno. But life, if it ever arose there, has remained hidden. No signal has reached us from those depths. No probe has passed by. We know of Methuselah only because its timing whispers through space. The pulsar it orbits ticks like a cosmic metronome, and the planet's presence perturbs the beat. From such delicate rhythms, we read the presence of a world that has seen almost the entire history of time. The strange thing is, the universe does not seem selective in its generosity. It makes planets easily, almost frivolously. It scatters them across billions of stars, forms them even around the corpses of stars, and lets them drift alone through interstellar space. There are rogue planets without suns, planets that formed and were flung away by violent reshufflings. These cold, sunless worlds may number in the billions within our galaxy alone. Some may retain heat for eons. Some may have thick atmospheres or oceans buried beneath frozen shells, warmed by radioactive decay. There is even a class of planets that may not orbit any star but glow faintly with heat from their formation, visible only to the most sensitive infrared instruments. These planetary ghosts haunt the void between stars, unmoored from any system, relics of instability. Their darkness hides their secrets. We know they exist. We do not yet know how many. And the universe continues to build. With every passing million years, new stars ignite, new disks form, new planets accrete. The current age of planet formation is not over. It is ongoing, especially in the spiral arms of galaxies like our own. And as each new planetary system emerges, the potential for life flickers anew. If life arises easily, it could be blooming on 1,000,000 worlds this very moment. If it is rare, those first worlds might still be the only cradles it has ever known. We cannot yet say. The data is too sparse, the distances too great, the signals too faint. But the search sharpens. Missions are planned, telescopes built, algorithms refined. The Habitable Worlds Observatory will one day look at exoplanets, not as abstract data points, but as places we can image, study, and dream about. We will analyze their skies for disequilibrium, the chemical fingerprints that suggest life interfering with chemistry, oxygen, methane, ozone, nitrous oxide. Any one of these might be produced by non-biological processes, but find them all together, in the right balance, and the case becomes stronger. If we find such a world, the implications are staggering. It would mean that life is not confined to Earth, that biology is not a cosmic fluke, that the universe is not silent, but singing life into being wherever conditions permit. It would not answer all our questions, but it would break the loneliness. It would change our story. And if we do not find such signals, if the skies of all surveyed planets remain quiet, their spectra unbroken by the telltale signs of breath and metabolism, then the mystery deepens. It could mean that life is truly rare, that intelligence is rarer still, that Earth is an anomaly. Or it could mean we are still early in our search, still unpracticed in interpreting the whispers of alien atmospheres. What we do know is that planets come easily. Life, perhaps less so. Civilization, rarer yet. And so each discovery pushes us to reflect not just on the cosmos, but on ourselves. If there are billions of planets, and we are alone among them, what responsibility does that confer? If we are not alone, how do we choose to meet that future? The universe is old. The stars burn with memories. Some planets may have watched galaxies collide, watched quasars blaze, watched the spiral arms of the Milky Way twist and reform. And if any life watched from those planets, it too witnessed a universe in motion, in drama, in ceaseless change. From the fire of early stars to the cold tranquility of rogue worlds, from gas giants wrapped in storms to rocky moons with oceans beneath their shells, the variety is staggering. Yet in that variety lies a kind of unity. The same laws of physics shape every world. The same elements combine in endless patterns. The same gravity binds every orbit. The cosmos is not chaotic. It is intricate. And so we listen, with radio waves, with infrared telescopes, with gravitational microlensing, with our models, our theories, and our hope. We listen to the stories planets tell, stories that began long before we were here, stories that may continue long after we are gone. For every world out there is a question. Did life begin? Did it last? Did it speak? And for every answer we find, we take one step closer to understanding our place in the vastness. Perhaps we are the cosmos becoming aware of itself. Perhaps we are just a flicker in the dark. But we are a flicker that looks outward. And in that looking, we become part of the story.
The universe balances itself upon a blade so fine that even the smallest tremor can send reality plunging into chaos. Everywhere we look in the cosmos, this delicate dance between structure and collapse plays out in breathtaking fashion. When magnetic energy surges within a star, it lashes outward as a solar flare that rips through the cold vacuum of space. When a supergiant begins fusing iron, it sets off a chain reaction so violent that the star unravels into a cataclysmic hypernova. And when pressure mounts within the crust of a spinning magnetar, the sudden crack of a starquake releases torrents of gamma radiation into the void. These moments are not merely dramatic events. They are cosmic tipping points, instances where matter and energy, pressure and temperature, order and entropy reach their critical thresholds. The entire universe, from the tiniest atoms to the sprawling clusters of galaxies, exists in a state of suspended equilibrium, and even the smallest disruption can ripple outward into profound transformations. And yet, miraculously, stability often reasserts itself. Subatomic safety nets emerge, hidden forces rally, and matter finds new forms to cling to. Like a cosmic version of Jekyll restraining Hyde, the universe somehow keeps its most destructive impulses in check at least most of the time. Nowhere is this tightrope more evident than in neutron stars. These are not just the remnants of stellar collapse, they are physics pushed to its breaking point. Imagine a star the size of a city, yet heavier than our sun, spinning dozens or even hundreds of times every second. Its gravity is so intense that if you were to drop something from shoulder height, it would reach half the speed of light before hitting the surface. Mountains here rise only fractions of a millimeter before the crushing gravity flattens them again, and the deeper one ventures into this stellar corpse, the stranger things become. The layers grow denser, the forces fiercer, and the laws of physics more tenuous. Understanding what happens inside neutron stars is not just an astrophysical curiosity, it is a gateway to understanding matter, space, time, and the very fabric of existence itself. Neutron stars are the last stronghold before matter folds in on itself completely. They are nature's ultimate experiment in extremity, a place where the universe tests its own limits, balancing on the razor's edge between endurance and collapse. To truly grasp these bizarre objects, we must start with the one star we know best, our Sun. On the night of December 24th, 2024, as families on Earth immerse themselves in the warmth of celebration, a spacecraft named the Parker Solar Probe was dancing through peril, traveling at 200 kilometers per second. It came within 6 million kilometers of the solar surface, closer than any human-made object has ever dared. That distance might seem vast, but in astronomical terms, it is as if the Parker Solar Probe had dipped a fingertip into the flames of a bonfire. It entered the corona, the Sun's outermost layer, a ghostly halo of superheated plasma that launches violent coronal mass ejections into space. These ejections are the sun's tempests, storms of ionized matter so powerful they can knock out satellites and power grids on Earth. Yet the corona is not the whole story. Below it lies the chromosphere, a thin layer of fiery gases at 5,000 degrees Celsius. Beneath that lies the photosphere, the layer we see from Earth, a boiling ocean of plasma where hot gases rise, cool, and sink again in a mesmerizing dance. But to unlock the mystery of why the sun burns and what it tells us about neutron stars, we must travel further back, not through space, but through time to colonial India in the early 20th century. Amid political upheaval and calls for independence, a teenager named Meghnad Saha found himself expelled from school for his role in protests against British rule. That same young man would go on to become a leading astrophysicist. In 1923, he developed the Saha ionization equation, a breakthrough that allowed scientists to calculate the degree to which various elements in a star are ionized based on local temperature and pressure. This was more than just a formula. It was a new way to read the sun's inner workings. Ionization is the process by which electrons are stripped from atoms, turning ordinary gases into plasma, the fourth state of matter. Most of us learn in school about solids, liquids, and gases. Plasma is the realm beyond, an electrically charged soup of subatomic particles. The photosphere of the sun is partially ionized, a mixture of gas and plasma. But as we dive deeper, the plasma becomes dominant. By the time we reach the core, we have entered a realm of unimaginable pressure. The temperature soars to 15 million degrees Celsius, and the density reaches 150 grams per cubic centimeter, 8 times denser than gold. In this inferno, hydrogen atoms are smashed together with such force that they fuse into helium, releasing immense amounts of energy. Every second, 620 million tons of hydrogen vanish, and 616 million tons of helium take their place. The missing mass is converted into energy, sustaining the sun's radiant glow. But this energy takes a long time to escape. On average, photons created in the core will take 170,000 years to fight their way to the surface. The balance between the outward pressure of this energy and the inward pull of gravity is what keeps the sun stable. This balance is known as hydrostatic equilibrium. Physicists describe this equilibrium using the equation of state, a formula that connects pressure, temperature, and density. In the sun, this equation is well understood, but things become more complicated as stars evolve. As they run out of fuel, the balance begins to falter. Gravity pushes inward with no opposition, and the star contracts. What happens next depends on the star's mass. Smaller stars become white dwarfs, stabilized by electron degeneracy pressure, a quantum force arising from the Pauli exclusion principle, which states that no two electrons can occupy the same state. The electrons resist being squeezed too close together, generating a pressure that halts the collapse. This was the insight of Ralph Fowler, whose wartime injuries led him to pivot from ballistics to astrophysics. Fowler's work laid the foundation for understanding white dwarfs and later, neutron stars. One of the most iconic white dwarfs is Sirius B, the pup, a companion to the bright star Sirius. Though no larger than Earth, Sirius B is more massive than the Sun. Its matter is so tightly packed that a sugar cube of it would weigh as much as an elephant. Such density should cause collapse. Yet degeneracy pressure holds it at bay. But even this quantum pressure has limits. Subramanian Chandrasekhar, building on Fowler's work, showed that if a white dwarf exceeds 1.4 solar masses, degeneracy pressure will fail and collapse will resume. This is the Chandrasekhar limit, the tipping point beyond which a white dwarf becomes a neutron star. In these more massive remnants, gravity crushes protons and electrons together to form neutrons. These, too, resist compression, thanks to neutron degeneracy pressure, offering one final buffer against total collapse. But what happens beyond this point, and what secrets lie buried in the heart of these neutron stars? That is the mystery we will begin to unravel in the chapters ahead. To study these cosmic balancing acts is to look into the fundamental nature of reality. Stars may burn and explode, collapse and flare, but always they reveal something about the rules that govern everything. And as we turn our gaze inward to the strange and powerful world of neutron stars, we begin to grasp the staggering question, how far can we push the universe before it breaks? The collapse beyond light. The tipping points that give birth to neutron stars are not isolated eruptions of energy, but part of a long and interconnected history of ideas, calculations, and revolutionary insights. Among the trenches of the First World War and the debris of fallen empires, a quiet intellectual revolution was stirring. When a French battleship disappeared beneath the waves in the Dardanelles in the spring of 1915, the headlines spoke of defeat. But in a hospital far from the front lines, a wounded soldier named Ralph Fowler began a transformation that would shift the course of theoretical astrophysics. His injury, suffered during the chaos of Gallipoli, led him to a new life among fellow scientists, where conversations and wartime improvisations laid the foundation for a new understanding of collapsed stars. The same bullet that pierced his shoulder ended a military career and opened the door to one of the most influential collaborations in modern science. Out of these connections, Fowler's curiosity began to pivot toward the stars. And by the 1920s, Fowler's work on quantum gases laid the groundwork for understanding the peculiar behavior of electrons squeezed into tight corners of space. This concept degeneracy pressure explained how white dwarfs resisted collapse. But it also planted a deeper question. What if gravity grew too strong, too relentless, even for this strange new pressure to resist? This puzzle was taken up by a young Indian astrophysicist named Subramanian Chandrasekhar. At just 19, aboard a ship sailing from India to Cambridge, he calculated the theoretical limit beyond which a white dwarf would be unable to resist gravitational collapse. This number 1.4 times the mass of the Sun became known as the Chandrasekhar limit. It was not just a mathematical threshold, it was a cosmic guillotine. Chandrasekhar's insight was met with skepticism. The idea that there existed a fatal weight limit for stars ran counter to prevailing beliefs. Among the most vocal critics was Arthur Eddington, one of the most prominent astronomers of the time, who believed the concept absurd. But physics does not yield to opinion, and eventually, the community recognized the significance of the limit. What followed next was an explosion in our understanding of stellar death. Stars above the limit could not become white dwarfs. Instead, they would collapse further, pushing beyond the realm of electrons and into a denser, more mysterious regime where protons and electrons combine to form neutrons. This new form of stellar remnant was compact beyond imagination. A white dwarf may be as dense as 1 billion kilograms per cubic meter, but a neutron star reaches densities 100 million times greater. A single teaspoon of neutron star matter weighs more than Mount Everest. This compression is so extreme that gravity reshapes the structure of matter itself, forcing it to become something altogether alien. The very existence of these stars challenges our most fundamental understanding of nature. To find one of the first physical clues of such bizarre objects, we look to the night sky. The Crab Nebula, a tangled mass of glowing gas and dust, marks the site of a supernova that lit up the skies in the year 1054. Ancient astronomers in China recorded the appearance of a new star, so bright it could be seen in daylight. But what they did not know is that deep within the center of this stellar shroud remained the collapsed heart of the exploded star. The core had been compacted into a neutron star, not just any neutron star, but one that spun rapidly, sending beams of radiation into space like a celestial lighthouse. Such spinning neutron stars came to be known as pulsars. They revealed themselves by their rhythmic flashes of light, first detected by radio telescopes in the 1960s. At the heart of the Crab Nebula, one such pulsar spins 30 times every second. And this is not even the fastest. Some rotate hundreds of times per second, their rotation preserved from the original spin of the massive star that gave birth to them. Like an ice skater pulling in their arms, the star's collapse accelerates the spin. But it is not only angular momentum that intensifies. The magnetic fields of neutron stars are also compressed and concentrated, reaching strengths that defy imagination. One neutron star's magnetic field can be 100 billion times stronger than that of a typical fridge magnet. In such extreme fields, physics becomes unpredictable. These stars are not simply objects. They are laboratories of fundamental forces. Yet even within their stability lies a question of limits. For just as white dwarfs had a maximum mass, so too must neutron stars. This realization led to the concept of the Tolman-Oppenheimer-Volkoff limit, a theoretical upper mass bound for neutron stars. If this limit is breached, not even neutron degeneracy pressure can withstand gravity's relentless pull. The star must collapse further. And the only known outcome of such a collapse is the formation of a black hole, a place where gravity overwhelms all resistance and not even light can escape. Neutron stars, then, are the final checkpoint before the abyss. Yet their interiors remain a mystery. We cannot see inside them, and the pressures and densities involved are impossible to replicate on Earth. To understand them, astronomers must rely on indirect evidence timing the pulses of pulsars, measuring their masses, analyzing their cooling rates, and watching for minute variations in their signals. One particularly revealing discovery came from the Neutron Star Interior Composition Explorer, or NICER, a telescope mounted on the International Space Station. NICER's precision allowed astronomers to map the surface of a pulsar by observing the way its X-rays fluctuated. These maps hinted at mountains mere millimeters tall and gravitational fields that bent light so strongly. The far side of the star became visible. Such observations allowed astronomers to measure not only the size of neutron stars, but also to test different equations of state models that describe how matter behaves at such unthinkable pressures. But even among neutron stars, there are outliers. One in particular, known as J0740, puzzled scientists. Despite having more than twice the mass of the Sun, it was no smaller than other neutron stars of lesser mass. This contradicted expectations. In theory, more massive neutron stars should be more compact. Their gravity should squeeze them tighter. Yet J0740 defied this logic. Its size suggested either a misunderstanding of the equation of state or the presence of exotic matter within. Perhaps, deep in its core, the neutrons break down into their constituent quarks, or maybe even stranger particles, hyperons containing strange quarks, begin to emerge, creating a new state of matter. These questions highlight the frontier that neutron stars represent. They are not just remnants of stellar death. They are crucibles where the rules of physics are tested, stretched, and sometimes broken. To study them is to touch the edges of what is knowable. In these cosmic collisions and quiet pulses, we glimpse the universe in its most extreme form, and as we prepare to journey deeper into their interiors, we ask once more what hidden forces hold back the night. The architecture of collapse. Beneath the crust of a neutron star lies a territory so alien, so physically extreme, that every law of classical matter is rewritten. Just below its surface sits an atmosphere barely 10 centimeters thick, an envelope of hydrogen and helium glowing at temperatures near 2 million degrees Celsius. But this fragile veil is deceiving. What lies beneath is a fortress of incomprehensible pressure. Within moments of entering the crust, the atoms are stripped of their electrons, and the nuclei find themselves suspended in a sea of free-floating particles, packed so tightly that even light struggles to escape. It is here that electrons, neutrons, and protons begin to form patterns that defy earthly analogies, twisting and weaving into configurations born not of chemistry, but of nuclear geometry. This strange, dense frontier gives rise to one of the most exotic materials ever theorized, nuclear pasta. At such extreme densities, the forces between nucleons, protons, and neutrons begin to create structures as oddly familiar as they are entirely unprecedented, like culinary analogies forged in a quantum forge. These layers of matter contort into gnocchi, spaghetti, and lasagna-shaped formations. This isn't whimsy. These terms refer to real theoretical arrangements predicted by sophisticated computer simulations. Spherical clusters form bubbles resembling gnocchi. Flattened sheets echo the stretch of lasagna. Long filaments curve through space like strands of spaghetti. This pasta, however, is not dinner table fare. It may be the strongest material in the universe, 10 billion times stronger than steel. Though no laboratory on Earth can reproduce these pressures, indirect evidence for the presence of nuclear pasta is mounting. The way neutron stars radiate heat, their spin-down rates, and sudden glitches in their rotation hint at structural rearrangements deep within. The rigidity of these pasta phases may even explain why neutron stars occasionally shudder in starquakes, a breaking of their internal architecture that releases bursts of radiation detectable across the cosmos. As we descend deeper, past the final folds of pasta, we encounter a domain where known matter begins to unravel. Neutrons, themselves once thought to be indivisible within stars, may begin to decay into their constituent parts. This realm remains hypothetical, but scientists believe that in the most massive neutron stars, pressure could become so great that even the neutrons lose their individual identities, dissolving into a fluid of quarks. Quarks are the fundamental particles that combine in threes to make up protons and neutrons. There are 6 known types: up, down, strange, charm, bottom, and top inside neutron stars. It is thought that only up and down quarks are typically present, but in extreme cores, strange quarks could emerge. This transformation yields what physicists refer to as quark matter, or more specifically, a quark-gluon plasma. In this state, the very building blocks of protons and neutrons slosh together in a sea of liberated particles, reminiscent of the conditions that existed in the first milliseconds after the Big Bang. These core regions would essentially host microcosmic echoes of the universe's earliest moment, a memory preserved in the heart of a dying star. But with this radical internal change comes an external paradox. If a neutron star becomes a quark star, an object made entirely of quark matter, then its density should increase further. This would, by gravitational logic, result in a smaller radius for more massive stars. Yet, observations like those of J0740 contradict this, implying that either quark matter behaves differently under pressure than expected, or that an entirely different form of matter exists at these depths. One such contender is dark matter. Though still elusive, dark matter is thought to comprise most of the universe's mass, exerting gravitational influence without emitting light. Some theorists propose that neutron stars, as they sweep through the galaxy, may scoop up dark matter, which then settles into their cores. If this dark matter interacts with itself or with baryonic matter, it could exert additional pressure or resist collapse in ways traditional models do not account for. This inclusion might help explain anomalously large neutron stars and open a new avenue for understanding both neutron stars and the universe's missing mass. Another theory gaining traction hinges not on exotic particles, but on quantum mechanics itself. Subatomic particles are defined not only by their mass and charge, but also by a quantum property called spin. Fermions, like protons and neutrons, have half-integer spin. And obey the Pauli exclusion principle, no two identical fermions can occupy the same quantum state simultaneously. This rule underpins degeneracy pressure. But bosons, particles with whole number spin, can share quantum states freely. If, under extreme conditions, fermions pair up to behave as composite bosons, they can collapse into a Bose-Einstein condensate, a state of matter where all particles move in concert as a single quantum entity. This possibility, though speculative, has profound implications. If the core of a neutron star transitions into a Bose-Einstein condensate, it may explain how these stars resist collapse even when exceeding conventional mass limits. It also reintroduces the name of Satyendra Nath Bose, the Indian physicist whose collaboration with Albert Einstein led to this prediction a century ago. In this way, the theoretical scaffolding of neutron stars ties back not only to astronomical observation, but to the deepest philosophical insights of quantum theory. Yet these stars remain mysterious partly because we cannot peel them open. We must rely on their emissions, on indirect measurements, and on the precise timing of the radiation they pulse into space. When two neutron stars collide, as happened in the event named GW 170817, we catch a rare glimpse into their interiors. The gravitational waves released carry information about their composition, while the light that follows from X-rays to gamma rays to visible light tells us about the debris. It is from these collisions that heavy elements like gold and platinum are forged. In a single explosion, the universe disperses its rarest treasures. All of this underscores a simple truth. Neutron stars are not merely remnants. They are living records of cosmic history, laboratories of extremes, and perhaps keys to unlocking fundamental truths about matter, gravity, and the evolution of the universe. They show us that at the edge of collapse, the universe invents new rules to hold itself together. The final barrier before the abyss. There is a boundary in the cosmos beyond which no force can resist collapse. If neutron stars are the last bastions against gravitational annihilation, then what happens when even they are pushed too far to understand this final tipping point? We must turn our gaze toward the darkest heart of astrophysics, where neutron stars can no longer hold their shape and instead fall into the abyss of black holes. But to reach that threshold, we must first examine how neutron stars walk their own perilous edge. The concept of a maximum mass for neutron stars, the Tolman-Oppenheimer-Volkoff limit, emerged in the early 20th century from minds struggling to quantify this final cosmic checkpoint. Early calculations placed this limit below the mass of the Sun, but modern refinements have pushed it closer to 2.2 solar masses, perhaps even higher. Anything beyond this and the neutron degeneracy pressure collapses like a scaffold torn from its foundation. The star succumbs to gravity in full, vanishing behind an event horizon from which no light can return. This transformation is not merely a continuation of stellar death, it is a redefinition of existence, where mass bends space-time so severely that even time itself seems to halt. But before crossing that threshold, neutron stars show signs of resistance. Some rotate at incredible speeds, and this spin helps counteract gravity. These millisecond pulsars, as they are called, generate centrifugal force that effectively adds structural support. The fastest spin measured so far exceeds 700 rotations per second, like a figure skater spinning faster as they draw their arms inward. These pulsars use angular momentum to delay collapse, but even spin has its limits. When accretion from a binary companion increases the mass of a neutron star too far, not even rapid rotation can forestall doom. The best evidence for the final mass limit came not from theory, but from observation. In 2017, the Laser Interferometer Gravitational Wave Observatory, or LIGO, detected a signal labeled GW170817. It came from the merger of two neutron stars, each roughly 1.4 times the mass of the Sun. When they collided, they did not immediately form a black hole. Instead, they produced a transient hypermassive neutron star that survived for mere moments before collapsing. The gravitational waves and the accompanying light burst allowed astronomers to narrow down the Tolman-Oppenheimer-Volkoff limit with greater precision. They now believe it lies between 2.1 and 2.3 solar masses. What happens when this limit is breached is astonishing. The neutron star, already more massive than the Sun and compressed into a sphere the size of a city, implodes. In a fraction of a second, it becomes a black hole. Its core contracts infinitely, forming a singularity, an object of infinite density and zero volume. Around this singularity, space itself is so warped that not even light can escape. The surface of no return is called the event horizon. Inside it, all paths lead inward. No message, no matter, no memory can pass outward again. And yet, this is where theory begins to fracture. General relativity, the framework that describes gravity, predicts this collapse with ruthless certainty, but quantum mechanics, the law book of the small, cannot accept infinities. According to quantum theory, singularities are mathematical monsters, signs that something in our understanding has gone wrong. This tension between the largest and smallest theories in physics fuels the search for quantum gravity, a unified theory that can describe what happens inside black holes. Neutron stars, teetering just above this brink, offer our best hope of finding that theory. Because their interiors reach conditions nearly as extreme as black holes just shy of total collapse, they represent nature's laboratory for testing new physics. If we can understand what matter does at these pressures, we might be able to avoid the infinities that plague singularities. Some theories propose that black holes are not singularities at all, but instead contain quark matter or even more exotic states. Others suggest that the cores of collapsing neutron stars might bounce, forming structures that mimic black holes but never fully become them. There are also quantum theories that challenge our assumptions about event horizons. Some posit that the intense information content of black holes results in firewalls' hypothetical regions of searing energy that would destroy anything falling in. Others suggest that quantum entanglement might allow information to leak back out, subtly encoded in Hawking radiation. But none of these ideas have been confirmed. They remain mathematical whispers, waiting for neutron stars and their death throes to speak the truth. The need for better understanding became urgent with the discovery of the most massive neutron star ever recorded, PSR J0952-0607. Weighing in at 2.35 solar masses, it appears to defy the supposed maximum limit. How can it exist? One answer may lie in its rapid spin, which could temporarily stave off collapse. Another possibility is that our equations of state the relationship between pressure, temperature, and density are still incomplete. If the matter inside neutron stars behaves differently than expected, perhaps they can support more mass. Some models now suggest that neutron stars might transform into entirely new classes of objects before collapsing into black holes. Among these hypothetical stars are quark stars, where matter exists not as neutrons, but as free-floating quarks. Others propose gravastars, where spacetime itself undergoes a phase change, creating a stable vacuum shell that halts collapse. These ideas are speculative but tantalizing, offering new ways to think about gravity and the limits of matter. Even more exotic are ideas linking neutron star interiors to dark energy, the mysterious force accelerating the expansion of the universe. If a form of dark energy exists inside neutron stars, it could produce repulsive pressure that helps resist collapse. This would not only explain unusually massive neutron stars, but also provide a direct connection between the tiniest and largest forces in the cosmos. And yet, all these questions return to a single point: what lies within. Neutron stars, by their very nature, hide their truths beneath layers of mystery. Their surfaces are calm, their pulses precise. But beneath that stillness lies the potential for transformation more violent and fundamental than any explosion. Their collapse is not just an ending, it is a threshold into the unknown. Stars that refuse to die. To follow the story of neutron stars to its end is to chase a paradox: how something so small can contain such immensity, and how something so still can harbor such violent potential. As we look deeper into the strange physics of these compact remnants, we find that they are not the end of stellar life, but rather a crucible for new beginnings. Their collapse challenges our best theories, but their very existence offers something extraordinary: a window into the unification of the laws of the universe. Perhaps no mystery better captures this contradiction than the case of neutron stars that are colder than expected. In the summer of 2024, a team of astronomers led by Alessio Marino at the Institute of Space Sciences in Barcelona studied the X-ray emissions of 3 seemingly ordinary neutron stars. Using the Chandra and XMM Newton space telescopes, they expected to measure surface temperatures in the predictable range for their ages. Instead, they found something shocking: all 3 were between 10 and 100 times colder than their peers. This chilling result immediately challenged the assumptions encoded in most equations of state. The rate at which a neutron star cools is dictated by its interior composition. If particles within are able to shed energy efficiently, especially by emitting neutrinos, then cooling can happen far faster than standard models predict. Neutrinos, those ghost-like particles born in the sun and forged in nuclear reactions, are perfect emissaries for carrying away energy, but the degree to which they escape depends entirely on what lies at the star's core. If hyperons are present, or if matter has transformed into a superfluid or a Bose-Einstein condensate, the cooling will change drastically. In this way, each cold neutron star becomes a kind of thermometer, and what Marino's team found forced theorists to revise, eliminate, or reweight entire classes of internal models. This is the heart of the multi-messenger era of astronomy, observing the universe not just in light, but through gravitational waves, neutrinos, and other signals that cross traditional boundaries. Since GW 170817, more neutron star mergers have been anticipated and observed, though few so far have matched its clarity. Still, with each event, our models are tested anew. The hope is that one day, a merger will occur close enough, or aligned just right, to let us observe the entire process from the first ripple in space-time to the final burst of gamma rays. In such a moment, the veil may lift. Meanwhile, particle physicists continue their work underground, beneath kilometers of ice or stone, watching for signs of what lies within these cosmic anomalies. In the Antarctic, the Ice Cube Neutrino Observatory waits for a high-energy neutrino that might be born in a neutron-star collision, or perhaps released in the collapse into a quark star. Other experiments attempt to simulate the pressures of neutron star cores using heavy ion collisions, briefly recreating conditions that existed moments after the Big Bang. And at the outermost limits of theory, physicists still dream of a deeper symmetry, one that combines general relativity and quantum mechanics into a single theory of everything. In this view, neutron stars are not curiosities but necessary guides. They compress mass and space into configurations that might act as test cases for string theory, loop quantum gravity, or other emerging frameworks. A neutron star may be as much a bridge to the quantum universe as the Large Hadron Collider. Their pulses, collisions, and cool silences may be datasets for the next generation of fundamental physics. There are even philosophers and cosmologists who see neutron stars as a kind of metaphor, the final act in a stellar drama, yet also a stage where the rules of the universe are rewritten. These stars are memory, fossil, and forge all at once. They remember their progenitor stars and preserve their angular momentum. They act as fossils, recording the gravitational behavior of matter under conditions unreproducible elsewhere. And they are forges, crafting the heavy elements that build planets, bones, and cities. In their silence, neutron stars speak volumes. The regular ticking of a pulsar's beam is the most precise clock in nature. Astronomers use pulsars to measure time better than atomic clocks, and to search for the slow rumble of gravitational waves from colliding galaxies. They are the metronomes of the cosmos, keeping time for an orchestra whose composition we have only just begun to decipher. And so the neutron star, once considered a dead end, becomes a new beginning. Its birth signals not just the death of a star, but the birth of insight. It connects thermodynamics to quantum mechanics, nuclear physics to cosmology, and the past of the universe to its future. In each of these collapsed stars is an unanswered question, a challenge to our hubris, a call to look deeper. One day, we may understand every layer of their interiors. One day, we may probe their cores with precision and map their magnetic fields in 3 dimensions. One day, we may even recreate neutron star conditions in the lab, or discover that their matter holds the key to dark energy or quantum gravity. Until then, we look to the skies and listen to their signals, aware that the most extreme objects in the universe may also be the most illuminating. Neutron stars remind us that the universe does not just explode, it compresses. It does not just create, it remembers. And it does not just end, it transforms. They are stars that refuse to die, and in their endurance, they may reveal to us what it means to exist at all.